Imagine a place where the universe itself is being ripped apart and stitched back together, where invisible forces shape entire galaxies and cosmic structures without anyone ever seeing them directly. These aren't just random explosions or bursts of energy. They're part of a fundamental process that sculpts the very fabric of the cosmos. And yet, despite their importance, most people have never even heard of them. Cosmic accretion shocks. If that name doesn't immediately send chills down your spine, you're not alone. They're one of the most mysterious and overlooked phenomena in astrophysics. These cosmic-scale shockwaves, triggered by the gravitational pull of forming galaxies and galaxy clusters, play a crucial role in the structure of the universe. They take in cold, diffuse gas from the vastness of intergalactic space, superheat it, and set the stage for everything from the birth of stars to the feeding of black holes. Right now, as you're watching this, unimaginable amounts of energy are being released across the cosmos by these very processes. But here's the kicker: no one has ever directly seen one of these shocks in action. We only know they exist by piecing together clues scattered across the universe, like cosmic detectives trying to solve a case that spans billions of years. What if I told you that without these accretion shocks, the universe as we know it wouldn't even exist? That stars, planets, and even life itself are byproducts of these powerful, invisible forces? And that understanding them might be the key to unlocking some of the biggest mysteries in astrophysics? This isn't just a theoretical exercise. Astronomers are actively searching for the smoking gun, direct evidence of cosmic accretion shocks shaping the universe on the grandest scales. But what exactly are these shocks? How do they form? And what do they mean for the evolution of the cosmos? To understand, we have to start with the basics: how galaxies and galaxy clusters form in the first place. Because if you think of the universe as a giant game of cosmic construction, then accretion shocks are the hammer and chisel sculpting the final product. At the heart of this mystery is something known as large-scale structure formation. The universe isn't just an empty void with a few scattered galaxies. Instead, it's filled with an intricate web-like structure called the cosmic web. This vast network is made up of filaments, long, thread-like structures composed of dark matter and gas. These filaments stretch across billions of light-years and serve as the scaffolding upon which galaxies and galaxy clusters form. But here's the thing: this gas isn't just sitting still. It's constantly moving, pulled inward by the immense gravity of forming galaxies and clusters. And when gas falls into these massive structures, it doesn't just smoothly settle in. Instead, it crashes into itself at supersonic speeds, creating shockwaves. These aren't like the shockwaves from an explosion on Earth. They're cosmic in scale, millions of light years across. When these shockwaves occur, they violently compress and heat the gas, pushing it to temperatures of millions of degrees. That's what we call a cosmic accretion shock. Why does this matter? Because this extreme heating process changes everything. Before the gas encounters the shock, it's cold and unable to form stars. But once it gets heated to extreme temperatures, it emits X-rays and radio waves, making it visible to astronomers. It also determines whether a galaxy or a cluster continues growing or stops accumulating more matter. In other words, accretion shocks are the gatekeepers of cosmic evolution. Now, to get a better picture of how this works, imagine a river flowing peacefully toward a waterfall. Before it reaches the edge, the water is calm and controlled. But once it reaches the drop, everything changes. Turbulence, chaos, and violent movement take over. That's exactly what happens when gas falls toward a galaxy cluster and encounters an accretion shock. It suddenly goes from being a quiet, drifting cloud to a roaring, superheated plasma. But this isn't just theoretical. Astronomers have seen indirect evidence of these shocks in galaxy clusters. For example, some of the largest known structures in the universe, like the massive galaxy clusters forming at the intersection of cosmic filaments, show clear signs of these violent transitions. Observations with X-ray telescopes like Chandra have revealed hot, shocked gas at the edges of these clusters, indicating that accretion shocks are shaping them in real time. Even more interesting, these shocks don't just heat gas. They also generate cosmic magnetic fields and accelerate particles to nearly the speed of light, creating high-energy cosmic rays that can travel across the universe. Some of the cosmic rays that eventually reach Earth, passing through our atmosphere, may have originated in these massive accretion shocks billions of years ago. But here's the biggest question: if these accretion shocks are so important, why is it so hard to see them directly? The answer lies in their vast size and the nature of the signals they produce. Unlike the bright explosions of supernovae or the dramatic spirals of galaxies, accretion shocks exist on a scale that's almost incomprehensible. Their signatures are faint, spread out across millions of light years, and require highly sensitive instruments to detect. That's why astronomers are turning to new methods to find them. One promising approach is searching for radio signals from shock-accelerated electrons. When electrons are pushed to extreme speeds by these shocks, they emit synchrotron radiation, a type of radio wave emission. Large radio telescopes, like the Square Kilometre Array, are now being used to scan the skies for these faint signals, hoping to catch accretion shocks in action. But there's still so much we don't know. How exactly do these shocks form in different environments? How do they influence star formation in galaxies? And could they even be linked to the formation of supermassive black holes? To answer these questions, we have to go even deeper, into the physics of shockwaves themselves. Because at their core, accretion shocks follow the same principles as explosions and shock waves we see on Earth, just on an unimaginably larger scale. When we talk about shock waves, we usually think of things like sonic booms from jets, explosions, or even the blast wave from a supernova. But at their core, all shock waves, including cosmic accretion shocks, follow the same fundamental physics. They form when a fluid, or in this case, intergalactic gas, moves faster than the speed of sound in that medium. When this happens, the gas can't simply adjust to its new surroundings smoothly. Instead, it experiences a sudden and violent compression, resulting in an abrupt change in pressure, temperature, and density. In cosmic accretion shocks, the gas isn't just moving fast, it's falling toward galaxy clusters at thousands of kilometers per second. These velocities are so extreme that when the gas finally slams into the dense environment of a forming cluster, it heats up to temperatures of tens or even hundreds of millions of degrees. This heating is what allows us to detect these shocks in X-ray and radio wavelengths. But let's take a step back. What actually causes these flows of gas in the first place? The answer lies in the very structure of the universe. The cosmic web is not a static thing, it's dynamic, constantly shifting as galaxies grow and merge. Gravity pulls matter inward, funneling gas along the filaments of the cosmic web toward denser regions. And when this inflow of gas reaches a galaxy cluster, it hits a dense, hot environment, creating the shock. Interestingly, there are actually two types of cosmic accretion shocks, strong and weak. Strong accretion shocks occur in the vast voids of intergalactic space, where the gas is still relatively cool. When this gas encounters a growing cluster, the sudden compression creates an intense shock that heats the gas dramatically. These are the most energetic and powerful accretion shocks in the universe. On the other hand, weak accretion shocks occur much closer to the centers of galaxy clusters. By the time the gas reaches this region, it has already been somewhat heated by previous interactions. As a result, the shock is less extreme, but it still plays a crucial role in regulating the flow of matter into the cluster. Both types of shocks have a profound impact on galaxy evolution. They determine how much gas is available for star formation, influence the growth of supermassive black holes, and even shape the large-scale magnetic fields that permeate the universe. Without these shocks, galaxy clusters wouldn't have the hot, X-ray emitting gas that we observe today. But there's still a major puzzle. How exactly do these shocks interact with dark matter? Dark matter makes up the majority of mass in galaxy clusters, but it doesn't behave like normal matter. It doesn't experience pressure or temperature changes like gas does, and it doesn't emit radiation. However, it does exert gravity, meaning that as dark matter collapses to form galaxy clusters, it pulls in gas along with it. This is what drives the formation of accretion shocks in the first place. Some simulations suggest that accretion shocks could actually be used to map out the distribution of dark matter. Since these shocks form at the boundaries of dark matter structures, Detecting them could give us clues about the shape and size of the invisible dark matter halos that surround galaxies and clusters. In other words, by studying accretion shocks, we might be able to indirectly see dark matter in action. But this raises another big question. Could cosmic accretion shocks be responsible for some of the unexplained high-energy phenomena we observe in space? For example, some of the most energetic particles in the universe, known as ultra-high-energy cosmic rays, have unknown origins. These particles travel at nearly the speed of light and carry so much energy that they shouldn't be able to travel across intergalactic distances without losing energy. Yet, we still detect them on Earth. Some astrophysicists believe that the extreme conditions in cosmic accretion shocks could be responsible for accelerating these particles to such high energies. If that's the case, then accretion shocks wouldn't just be shaping galaxies. They'd also be influencing fundamental cosmic processes that affect the entire universe. But here's where things get even weirder. Recent observations have hinted at something unexpected. Some galaxy clusters seem to have shock waves that extend far beyond what we would expect from normal accretion processes. These extended shocks suggest that something even more powerful might be at play. One possibility is that these are relics of past mergers between massive galaxy clusters. When two clusters collide, the energy released is enough to create massive shock waves that ripple outward, heating the surrounding gas and altering the entire structure of the cluster. These merger-driven shocks are some of the largest known structures in the universe, stretching across millions of light-years. But could there be something even more exotic going on? Some researchers have proposed that these extended shock structures could be linked to exotic new physics. Perhaps even the interaction between normal matter and dark energy, the mysterious force driving the accelerated expansion of the universe. If that turns out to be the case, then cosmic accretion shocks might not just be a side effect of galaxy formation. They could be a fundamental key to understanding the deepest mysteries of the cosmos. If cosmic accretion shocks hold the key to understanding dark energy, that would be a game changer. Dark energy is one of the greatest unsolved mysteries in physics. It's the invisible force responsible for the accelerating expansion of the universe, but we have almost no idea what it actually is. Scientists suspect it makes up about 68% of the total energy in the universe. But unlike dark matter, which has gravitational effects we can observe, dark energy doesn't clump together or form structures. It just pushes space apart. But here's where things get interesting. Some theoretical models suggest that dark energy might not be completely uniform across the universe. Instead, it could interact with normal matter in ways we haven't yet detected. If that's the case, then cosmic accretion shocks, where normal matter, dark matter, and the overall structure of space itself come together in extreme conditions, might reveal signs of this interaction. For example, if dark energy exerts even a tiny force on normal matter, then it could subtly alter the shape and position of these shocks over time. By mapping accretion shocks in different regions of the universe, and seeing if they behave differently than expected, we might find evidence of dark energy's hidden influence. Some researchers have even proposed that the edges of cosmic shocks could act as lenses that bend light in unusual ways due to dark energy's effects on spacetime itself. This would be an incredible breakthrough because, right now, most of what we know about dark energy comes from studying the large-scale expansion of the universe. If we could study its effects on individual cosmic structures like galaxy clusters, we might be able to figure out whether dark energy is truly a constant force or if it evolves over time. But beyond dark energy, cosmic accretion shocks might also have another unexpected connection to the mysterious cosmic voids. Cosmic voids are the opposite of galaxy clusters. They're enormous, empty regions of space, often spanning hundreds of millions of light-years, where very few galaxies exist. These voids are surrounded by the dense filaments of the cosmic web, and just like gas falls into galaxy clusters, gas also flows out of these voids toward denser regions. Some researchers believe that cosmic accretion shocks might actually play a role in shaping the boundaries of these voids. As gas is pulled away from the voids and into the surrounding cosmic filaments, shock waves could form along the edges of these voids, creating distinct boundaries between empty and dense regions of the universe. If true, This means that cosmic accretion shocks might be responsible for shaping not just the most crowded regions of the universe, but also the most desolate ones. But here's a question: if cosmic accretion shocks are so crucial to how galaxies and clusters evolve, could they also influence the fate of entire galaxies? The answer seems to be yes. One of the biggest challenges in astrophysics is understanding why some galaxies stop forming stars while others continue to grow. We know that galaxies need cold gas to form new stars. But in massive galaxy clusters, we often see galaxies that have run out of star-forming gas and have become red and dead, elliptical galaxies. One possibility is that cosmic accretion shocks are responsible for this process. When a galaxy falls into a large cluster, it doesn't just pass through undisturbed. Instead, it slams into the hot, shocked gas surrounding the cluster, a process known as ram pressure stripping. This can strip away a galaxy's gas, preventing it from forming new stars and effectively shutting down its evolution. But even for galaxies that aren't falling into clusters, accretion shocks could still play a role in regulating star formation. If a galaxy's inflowing gas encounters a shock before it reaches the galaxy, the gas will get heated to high temperatures, making it harder for the galaxy to pull it in. This means that accretion shocks might be one of the reasons why some galaxies stop growing while others continue to form stars. And it doesn't stop there. Some studies suggest that accretion shocks might even influence the activity of supermassive black holes at the centers of galaxies. We know that these black holes can grow by pulling in surrounding gas. But if accretion shocks heat up the gas before it reaches the black hole, it could slow down this feeding process. This means that cosmic accretion shocks might not just shape the outer structure of the universe, but also play a role in controlling the most extreme objects in existence, supermassive black holes. But there's still one final mystery. What happens to these shocks over billions of years? Do they continue shaping galaxy clusters forever, or do they eventually fade away? Right now, simulations suggest that accretion shocks should persist for the entire lifetime of a galaxy cluster, but their strength might change over time. Early in the universe, when galaxy clusters were still forming, these shocks were likely much stronger. But as the clusters grew larger and more stable, the shocks might have weakened, becoming less dramatic but still influencing the flow of gas. Some researchers even suspect that some of the most massive clusters we see today might have once had much stronger accretion shocks that have since faded, leaving behind only subtle traces. If we could find a way to study how these shocks evolve over cosmic time, it could help us understand how galaxy clusters, and the universe itself, have changed over billions of years. But for now, one thing is clear: cosmic accretion shocks are one of the most important, yet overlooked, forces shaping the universe. From heating gas to influencing star formation, from accelerating cosmic rays to possibly revealing the nature of dark energy, these massive shock waves are far more than just a side effect of galaxy formation. They are a fundamental part of the cosmic story, and as we develop more powerful telescopes and simulations, we are only beginning to understand their true significance. As we continue to dive deeper into the mysterious role of cosmic accretion shocks, we begin to realize just how integral they are to the very structure and evolution of the universe. These shocks, as powerful as they are subtle, influence not only the gas and galaxies around them but the very forces that govern cosmic growth on the grandest scale. One of the most fascinating aspects of accretion shocks is their impact on the cosmic magnetic fields. Magnetic fields, though invisible to the naked eye, permeate every corner of the universe, from the smallest particles to the largest galactic structures. They play a crucial role in guiding the flow of charged particles, and their behavior can reveal a lot about the physics of a region. It's now understood that accretion shocks are one of the primary mechanisms by which magnetic fields are amplified in galaxy clusters. As gas collides with the shock waves, its motion and the compression of matter can stretch and twist magnetic field lines, increasing their strength. This process, known as magnetic field amplification, can create some of the most intense magnetic fields in the universe, especially in the regions around galaxy clusters. These amplified magnetic fields play a crucial role in the cosmic ecosystem. For one, they help accelerate cosmic rays, those ultra-high energy particles that travel through space at nearly the speed of light. When charged particles are funneled along these magnetic field lines, they can be accelerated to mind-boggling speeds, sometimes reaching energies that far exceed anything we can replicate on Earth. In addition to cosmic rays, these magnetic fields influence the dynamics of the hot, X-ray emitting gas that fills galaxy clusters. The gas itself can become magnetized, creating a turbulent environment that might affect the cluster's overall behavior. This magnetization could be a key player in the way matter is distributed and flows within clusters, determining how galaxies within them evolve. And yet, the role of magnetic fields in cosmic accretion is still one of the great unsolved mysteries. We have only just begun to observe and understand how these fields interact with shocks on such a large scale. However, it's becoming increasingly clear that magnetic fields and accretion shocks are intimately linked in shaping the universe. Now, let's zoom in a bit further and consider what happens when two galaxy clusters collide. These catastrophic events, known as cluster mergers, are some of the most violent occurrences in the cosmos. The process of cluster mergers is not only responsible for creating some of the most massive shock waves in the universe, but it also serves as a powerful laboratory for understanding the behavior of accretion shocks. During a merger, two clusters of galaxies collide at speeds of up to 1,000 kilometers per second. As the two clusters merge, their gas and dark matter interact, creating enormous shock fronts that expand outward. These shock fronts heat up the gas to such high temperatures that the surrounding gas emits X-rays, which astronomers can detect. The energy released in these mergers is so vast that it can even create turbulence in the surrounding gas, driving currents of hot plasma throughout the cluster. In fact, some of the most impressive cosmic shock waves have been detected in regions where galaxy clusters are merging. One of the most famous examples is the Bullet Cluster, a pair of galaxy clusters that collided in the past. The collision of these two clusters created a shock wave so intense that it left behind an imprint of dark matter, helping scientists directly map out the distribution of dark matter in the universe. The shock waves produced by these collisions are not only crucial for our understanding of cosmic structure formation but are also key in determining how gas behaves in these extreme environments. Cluster mergers are also one of the few places where we can directly observe how cosmic accretion shocks affect the large-scale motion of matter. These massive events shed light on how the gas within clusters is distributed and how it responds to shock heating. It's in these high-energy environments that we can better understand the role of cosmic accretion shocks in galaxy cluster evolution. But even with all that we know about the gas and the magnetic fields, there's still one more major aspect that cosmic accretion shocks influence: galactic evolution. This goes beyond simply heating up the gas or creating magnetic fields. Accretion shocks directly affect how galaxies grow, how they form stars, and how they evolve over time. In fact, shock waves might even be responsible for some of the strangest phenomena in galaxy evolution. Take the example of the massive elliptical galaxies found at the centers of large galaxy clusters. These galaxies are often much older and less active than other galaxies. They are referred to as red and dead galaxies because they have long since exhausted their gas supply and no longer form new stars. Instead of continuing to grow through star formation, these galaxies might have been shut down by the shock heating of the gas around them. When a galaxy falls into a larger cluster, the gas surrounding it is often heated to such high temperatures by accretion shocks that it becomes unable to cool down and collapse to form new stars. This process, known as feedback, is one of the primary reasons why some galaxies stop forming stars altogether. It's a perfect example of how accretion shocks play a direct role in regulating galaxy growth, by preventing further gas from falling into the galaxy and by heating up the existing gas to prevent star formation. But it doesn't just stop there. In some cases, cosmic accretion shocks can actually trigger the formation of new stars. When gas is funneled into a galaxy from the surrounding cluster, it can encounter a shock that compresses it enough to trigger star formation. This happens in what's known as a cool core, a region where the gas is relatively cool but still dense enough to form stars. These starburst galaxies are often seen in regions where the shock waves from accretion are at their peak. These star-forming events show just how complex and multifaceted the role of cosmic accretion shocks can be. They aren't simply destructive forces. They can also be sites of new beginnings, where new stars are born even as older galaxies lose their vitality. As we continue to study these cosmic shock waves, we are slowly piecing together a much larger story about the evolution of galaxies, clusters, and even the universe itself. By mapping these shocks and understanding their effects on gas, magnetic fields, dark matter, and galaxy formation, we are opening the door to a deeper understanding of the universe's most profound mysteries. Looking to the future, the role of cosmic accretion shocks is bound to grow even more significant. New telescopes and advanced simulations are allowing us to study these shocks with ever greater precision. We are learning more about how they heat the gas that fills the vast cosmic web, how they regulate the flow of matter across the universe, and how they influence the growth of the most massive structures in the universe. Cosmic accretion shocks are more than just a phenomenon of cosmic growth. They are a fundamental part of the universe's blueprint. From shaping the gas that fills galaxy clusters to influencing the growth of stars and galaxies, these shock waves play a crucial role in determining how the universe evolves. Understanding them is one of the keys to unlocking the secrets of the cosmos and piecing together the grand story of the universe. As we continue our exploration into the profound impact of cosmic accretion shocks, we enter even deeper layers of understanding. The more we observe, the more apparent it becomes that these shocks aren't just a passive consequence of cosmic events, but a dynamic force that actively shapes the universe. From the first moments after the Big Bang to the present day, cosmic shocks have been continuously molding the structure of galaxies, clusters, and even the vast cosmic web that holds everything together. To truly comprehend the full scope of their influence, we must broaden our perspective and consider how accretion shocks interact with other cosmic phenomena. One of the most significant connections is with dark matter. While dark matter itself remains elusive and largely undetectable by traditional means, its presence is inferred through its gravitational influence on visible matter. Accretion shocks are thought to play an important role in how dark matter interacts with ordinary matter, specifically in the formation and evolution of galaxy clusters. When galaxies and clusters form, they pull in both regular matter, gas, dust, and stars, and dark matter. It's in these processes that accretion shocks become essential in understanding how dark matter behaves. Dark matter doesn't interact with electromagnetic forces, meaning it doesn't emit light or radiation that we can observe directly. However, its gravitational influence is evident, and it's believed that as matter collapses into clusters, dark matter gets trapped in these structures as well. What's fascinating here is that as the shock waves from accretion compress and heat the gas within galaxy clusters, the behavior of dark matter may change. There are competing theories about how dark matter and shocks interact, but one prevailing idea is that dark matter may be heated during these accretion events, although to a lesser extent than the gas. This subtle heating could influence the distribution of dark matter, contributing to the development of complex structures in the universe. In other words, cosmic accretion shocks may be indirectly responsible for how dark matter clumps together in the regions around galaxy clusters, further shaping the large-scale structure of the cosmos. These shocks could even play a role in determining the rate at which galaxies form within clusters, as they provide the framework for how gas and dark matter interact. Another profound consequence of cosmic accretion shocks is their effect on galaxy formation. As clusters form and evolve, the gas within them undergoes various phases, each one influenced by shocks of different scales and strengths. The ongoing heating of this gas by accretion shocks can suppress or encourage star formation, depending on the situation. For example, in the heart of some galaxy clusters, the gas is heated to such extreme temperatures that it cannot cool down and condense to form stars. This is known as suppressive feedback, where the shock-heated gas keeps galaxies from forming new stars, essentially halting their growth. This phenomenon explains why certain galaxies, especially the large, elliptical galaxies found in the cores of clusters, are often red and dead. They've stopped forming new stars, and their growth has essentially plateaued. On the flip side, accretion shocks can also facilitate the formation of new stars. When gas falls into a galaxy, it can encounter a shock wave that compresses the gas enough to trigger the birth of new stars. These starbursts typically happen in regions of the universe where gas is flowing inward and accreting onto galaxies at high rates. The shock compression of this gas ignites a flurry of star formation, producing new generations of stars. The relationship between accretion shocks and star formation is thus a dynamic and dual one, sometimes quenching star formation, other times spurring it on in a spectacular display. The delicate balance between suppressing and promoting star formation through cosmic shocks is just one part of the story. Over time, these processes can lead to the diversification of galaxies. While some galaxies in the centers of clusters may become older and redder, others, influenced by different shock dynamics, may continue to evolve, forming new stars and increasing in size. These evolutionary differences highlight just how important shocks are in shaping the long-term trajectory of galaxies. Another crucial facet of cosmic accretion shocks is their role in fueling supermassive black holes. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way, are believed to play a central role in regulating the growth and evolution of their host galaxies. The interplay between accretion shocks and supermassive black holes is an area of intense interest to cosmologists. When gas falls into a galaxy and interacts with the supermassive black hole at its center, the black hole can feed on this gas, growing larger over time. However, this accretion process isn't always smooth. It's thought that cosmic shocks can influence the way gas accretes onto these supermassive black holes. In some cases, shocks may drive gas away from the black hole's vicinity, stalling or suppressing accretion. In other cases, the shock waves might funnel gas directly toward the black hole, fueling its growth. This feedback loop between accretion shocks and black hole growth has profound implications. It's believed that supermassive black holes might play a role in the regulation of galaxy growth by limiting the amount of gas available for star formation. Through a process known as AGN feedback, active galactic nucleus feedback, a black hole's immense energy output can heat up surrounding gas, preventing it from cooling down and forming new stars. This adds yet another layer of complexity to the relationship between shocks, gas, and the evolution of cosmic structures. As we push the boundaries of our knowledge and delve deeper into the dynamics of cosmic accretion shocks, we are beginning to unlock the fundamental forces that have shaped the universe since its earliest days. Each discovery adds a new piece to the puzzle, offering a clearer picture of how galaxy clusters, galaxies, and even the smallest building blocks of the universe have been sculpted by these invisible forces. Looking ahead, we are entering an exciting era of discovery. The next generation of telescopes, such as the James Webb Space Telescope, will allow us to peer deeper into the universe than ever before. By observing how accretion shocks evolve and impact the structures they influence, we will gain even more insight into the mechanisms that govern the formation of galaxies, clusters, and the large-scale cosmic web. But there is still much we don't know. While we have made significant strides in understanding the role of accretion shocks in the cosmos, there are countless unanswered questions. For instance, how exactly do these shocks drive the evolution of the intergalactic medium, the vast, almost invisible expanse of gas that connects galaxies and clusters? What role do they play in the formation of the first galaxies, shortly after the Big Bang? And how can we better model and simulate these complex processes to predict their behavior over time? Despite the many mysteries that remain, one thing is certain: the study of cosmic accretion shocks is essential for understanding the fundamental nature of the universe. These phenomena, seemingly invisible and fleeting, have shaped the cosmic landscape over billions of years. They have sculpted the galaxies, clusters, and vast regions of space that we observe today. And as our observational tools continue to improve, our understanding of these cosmic shock waves will continue to evolve, revealing more about the forces that have shaped the universe. Ultimately, cosmic accretion shocks are not just a byproduct of cosmic evolution, they are its architects. They shape the very fabric of the universe, from the formation of stars and galaxies to the behavior of dark matter and the evolution of black holes. As we continue to study these remarkable phenomena, we may uncover even more startling truths about the universe's past, present, and future. One thing is clear: the role of cosmic accretion shocks will remain central to the story of the cosmos for years to come. The mysteries of cosmic accretion shocks stretch far beyond the edges of our current understanding. As we move forward in our exploration, one of the most fascinating aspects that remain to be unraveled is their potential connection to the very early stages of the universe. The formation of structures in the universe, like galaxy clusters and massive superstructures, appears to be deeply intertwined with these shocks, and understanding them could help us rewrite the narrative of cosmic evolution. To comprehend the role of accretion shocks in the early universe, we must consider how they might have influenced the first objects to form after the Big Bang. The universe, in its infancy, was a hot, dense place where matter was in a constant state of flux, rapidly cooling and expanding. As the first stars and galaxies began to take shape, accretion processes likely played a crucial role. The shock waves that formed during the collapse of primordial gas clouds might have been the key mechanisms that set the stage for the first galaxies and supermassive black holes. In the early universe, as gas was funneled into forming galaxy clusters, it would have experienced intense compression and heating from accretion shocks. These shocks not only heated the gas but also influenced its composition and distribution. By studying the remnants of these ancient shocks, such as the thermal properties of the gas left behind, scientists can gain valuable insights into the processes that led to the formation of galaxies, stars, and black holes. One area of active research in this domain involves the study of cosmic reionization. This period, which occurred about 1 billion years after the Big Bang, marks the time when the first stars and galaxies began to shine brightly enough to ionize the surrounding hydrogen gas. The interaction between shock waves from accreting gas and this ionized hydrogen would have been crucial in shaping the evolution of the universe during this epoch. Shock waves also played a significant role in shaping the larger-scale structures that define the universe today. The cosmic web, a vast and intricate network of galaxies, galaxy clusters, and filaments of dark matter, is thought to have formed through the process of cosmic accretion. Shocks generated by the accretion of gas onto these cosmic structures provided the necessary energy to build and sustain the web's complex shape. Understanding how shocks shape the cosmic web also opens up new possibilities for studying dark energy. The acceleration of the universe's expansion is a key feature of the cosmic landscape, and it is believed that dark energy, an unknown force responsible for this acceleration, may have been influenced by accretion shocks. As the gas within clusters is compressed and heated, the resulting shock waves could have contributed to the formation of cosmic voids and other large-scale features of the universe. The interaction between these shock waves and the mysterious force of dark energy could offer new avenues for research into the nature of the universe's expansion. Cosmic accretion shocks are also integral to our understanding of high-energy phenomena, such as the creation of cosmic rays and the behavior of black holes. The gas that falls into black holes often undergoes immense compression and heating, leading to the emission of high-energy radiation and particles. These shocks produce some of the most energetic events in the universe, releasing vast amounts of energy that can be detected across light years of space. It is important to note that these high-energy processes, driven by accretion shocks, are not just random occurrences. They are intimately connected to the evolution of galaxies and clusters. The energy released by black holes and other high-energy sources influences the surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism helps maintain the stability of galaxy clusters, ensuring that they don't collapse under their own weight. As we look deeper into the role of shocks, we must also consider the impact of these phenomena on the intergalactic medium. The space between galaxies is not empty but is filled with diffuse gas, often referred to as the intergalactic medium, IGM. This gas is heated and shaped by accretion shocks, which can alter its density, temperature, and chemical composition. The IGM plays a critical role in the ongoing evolution of the universe, as it connects the different components of the cosmic web and facilitates the exchange of energy and matter between galaxies. One of the most intriguing aspects of the IGM is its relationship with the cosmic microwave background (CMB) radiation, the afterglow of the Big Bang. The CMB provides a snapshot of the early universe, and studying how it interacts with the gas in the IgM could provide crucial insights into the conditions that existed during the universe's first few 100,000 years. As shocks continue to heat and compress this gas, their impact on the CMB may provide new clues about the origins of cosmic structure. Furthermore, the study of cosmic accretion shocks opens up exciting possibilities for future space missions. The upcoming launch of next-generation space telescopes and instruments will provide us with unprecedented views of distant galaxies and clusters. These observations could allow scientists to track the evolution of cosmic accretion shocks in real time, offering a closer look at how they influence the formation and behavior of galaxies, black holes, and other celestial phenomena. One of the most ambitious future goals in this field is to understand how accretion shocks influence the evolution of galaxy clusters over billions of years. By analyzing the energy and distribution of these shocks, scientists aim to uncover the processes that determine the size, shape, and structure of these massive cosmic systems. This knowledge could provide crucial insights into the ultimate fate of galaxy clusters, helping us understand whether they will continue to grow or eventually reach a state of equilibrium. The role of accretion shocks in the broader cosmic narrative also extends to the study of galaxy mergers. When galaxies collide and merge, the resulting shock waves can trigger bursts of star formation and redistribute gas, altering the evolution of both galaxies. These mergers play a pivotal role in the growth and evolution of galaxy clusters, and understanding the shock processes involved can shed light on how galaxies transform over cosmic time. As we continue to refine our models of cosmic accretion, we are also discovering new connections between these shocks and other mysterious phenomena. For example, recent research has suggested that accretion shocks might be linked to the formation of certain types of exotic objects, such as magnetars and strange quarks. These strange and rare objects could hold the key to unlocking some of the most profound mysteries of the universe. Looking forward, the study of cosmic accretion shocks promises to be a frontier of cosmic discovery. Every new observation and breakthrough brings us one step closer to understanding the intricate processes that govern the evolution of galaxies, clusters, and the very structure of the universe itself. In the coming decades, the role of shocks in cosmic evolution will likely become one of the most critical areas of study in astrophysics, providing us with a deeper understanding of the universe's past, present, and future. And as we peer into the cosmos, we are reminded that there is still so much we don't know. The universe is vast, mysterious, and constantly evolving, and the study of cosmic accretion shocks will undoubtedly continue to be a key part of our journey to uncover the fundamental forces that shape our reality. From the formation of stars to the birth of galaxies and the evolution of supermassive black holes, these shock waves are at the heart of some of the most intriguing and unexplained phenomena in the universe. As we continue to delve deeper into the subject of cosmic accretion shocks, the complexity of these phenomena becomes increasingly evident. The more we uncover about their role in the cosmic tapestry, the more we realize how much their effects influence not only the structure of galaxies and clusters but also the very fabric of the universe. The connection between accretion shocks and cosmic evolution is profound, as they dictate the temperature, density, and even the rate at which stars form in galaxies. Accretion shocks are not just important for understanding the formation of galaxies or clusters. They also have a direct impact on the cosmic feedback loop, the ongoing exchange of energy and matter between stars, galaxies, and their surroundings. This feedback loop is crucial in regulating star formation and the evolution of galaxies. As gas and matter are pulled into the gravitational well of a galaxy, they encounter shock waves that can prevent further star formation by heating the surrounding gas. This process, known as thermal feedback, ensures that galaxies don't grow too rapidly or collapse under their own weight. At the same time, these shock waves also have the opposite effect in certain situations, encouraging star formation under the right conditions. For instance, when galaxies interact or merge, the shock waves triggered by these events can compress gas clouds, leading to the birth of new stars. This feedback mechanism is essential for the balance of energy in the universe and plays a key role in the life cycle of galaxies. When considering the grand scale of cosmic evolution, the role of accretion shocks in galaxy cluster formation is even more intriguing. Clusters of galaxies are among the largest structures in the universe, and understanding how they form and evolve is essential to understanding the history of the cosmos. The gas that fills these clusters, known as the intracluster medium, ICM, is primarily heated by accretion shocks. These shock waves provide the energy necessary to sustain the high temperatures in the ICM, which can reach tens of millions of degrees. The ICM is often observed in X-ray wavelengths because it is so hot that it emits intense radiation. By studying the X-ray emissions from galaxy clusters, astronomers can map the distribution and properties of the hot gas and better understand the processes at play in these cosmic environments. The temperature and density variations within the ICM provide valuable clues about how accretion shocks are shaping the evolution of clusters and galaxies within them. Another important aspect of accretion shocks is their potential to influence the creation and growth of supermassive black holes at the centers of galaxies. These black holes are believed to form as gas and matter accumulate in the center of a galaxy, and the energy released by accretion shocks could play a major role in their development. The gas surrounding a black hole can be heated to extreme temperatures by these shocks, resulting in the emission of powerful radiation, including X-rays and gamma rays. The interplay between accretion shocks and supermassive black holes is a topic of intense research, as understanding this relationship could help us learn more about the behavior of these enigmatic objects. For example, we know that supermassive black holes can have a profound effect on their host galaxies, regulating star formation and even halting it entirely through powerful jets of energy and matter. These jets, which are created by material being drawn into the black hole, can interact with surrounding gas, producing shock waves that further influence the environment of the galaxy. The role of cosmic accretion shocks is not limited to the immediate surroundings of galaxies and clusters. As gas is funneled into these systems, it can interact with the vast stretches of the intergalactic medium, IGM. The IGM is the diffuse gas that exists between galaxies, and it is thought to play an essential role in the evolution of large-scale cosmic structures. As accretion shocks propagate through this gas, they heat and compress it, altering its properties and contributing to the formation of galaxy filaments and voids, the large-scale structures that define the cosmic web. The impact of accretion shocks on the IGM could also have significant implications for our understanding of dark matter and dark energy. The mysterious force that makes up the majority of the universe's mass and energy remains one of the most profound questions in astrophysics. While dark matter is thought to be responsible for the formation of galaxies and clusters, dark energy is believed to be driving the accelerated expansion of the universe. The interaction between accretion shocks and these invisible forces could provide critical insights into their nature and how they influence the universe's expansion. What makes the study of cosmic accretion shocks even more compelling is their connection to some of the universe's most extreme and violent events. When black holes or neutron stars form, they often release powerful shock waves that propagate across the universe, sending ripples through space-time. These shock waves are capable of distorting the fabric of space-time itself, creating gravitational waves that can be detected by specialized observatories such as LIGO and Virgo. Gravitational waves, which were first directly detected in 2015, provide a unique way to study the effects of these cosmic events, allowing us to gain insight into some of the most distant and energetic phenomena in the universe. The study of accretion shocks and their relationship to gravitational waves is a rapidly developing field of research. By analyzing the signals produced by these waves, scientists can learn about the formation and evolution of black holes, neutron stars, and other exotic objects. These studies are helping to shed light on the nature of space-time itself and may one day reveal new insights into the fundamental laws of physics. In addition to their connection to gravitational waves, accretion shocks also play a key role in the creation of cosmic rays, high-energy particles that travel through space at nearly the speed of light. These cosmic rays are believed to originate from the shock waves produced by supernova explosions, active galactic nuclei, and other high-energy phenomena. When cosmic rays collide with particles in the interstellar medium, they can produce a range of secondary particles and radiation, including gamma rays and neutrinos. Cosmic rays are of great interest to scientists because they provide a window into the most energetic processes in the universe. By studying these particles, researchers can gain a better understanding of the mechanisms behind accretion shocks and other high-energy phenomena. Cosmic rays are also thought to play a role in the formation of new elements in the universe, contributing to the process of nucleosynthesis. As we continue to uncover the mysteries surrounding cosmic accretion shocks, the field of astrophysics is evolving rapidly. Each new discovery provides more context for understanding the intricate processes that shape the universe, from the formation of galaxies to the creation of supermassive black holes and the distribution of dark matter and dark energy. One of the most exciting developments in this field is the increasing precision of observational techniques. With the advent of next-generation telescopes, such as the James Webb Space Telescope, and the growing number of space-based observatories focused on X-ray and gamma-ray astronomy, scientists are gaining an unprecedented ability to observe and study cosmic shocks in real time. These advancements are providing a wealth of new data, which is reshaping our understanding of the universe and opening up new frontiers in cosmic exploration. The future of cosmic accretion shock research holds incredible promise, with the potential to answer some of the most fundamental questions in astrophysics. As we learn more about the role of these shocks in shaping the universe, we will undoubtedly gain deeper insights into the forces that govern the cosmos, from the birth of galaxies to the behavior of the most extreme objects in space. In the coming decades, as our instruments become more advanced and our understanding of the universe deepens, the study of cosmic accretion shocks will continue to be a cornerstone of astrophysical research. These shocks may be the key to unlocking many of the universe's greatest mysteries, from the origins of galaxies and clusters to the nature of dark matter and dark energy. In the grand scheme of cosmic exploration, accretion shocks offer a glimpse into the very heart of the universe's most significant processes, those that shape its evolution on the largest scales. By continuing to study and explore these shocks, we may one day uncover answers to questions that have long eluded us, giving us a deeper understanding of the universe we inhabit. As we dive further into the role of cosmic accretion shocks, it becomes clear that these phenomena are far more than mere byproducts of cosmic activity. They are, in fact, fundamental drivers of the processes that govern the universe's evolution. Understanding how shocks interact with the matter and energy surrounding them can provide insight into the mechanics of cosmic structure formation, from the smallest galaxies to the largest galaxy clusters. One of the most striking aspects of accretion shocks is their ability to regulate the amount of gas and matter that flows into a system, influencing the growth of galaxies and clusters over time. This process, known as accretion feedback, plays a critical role in controlling the pace at which these structures evolve. Shocks are capable of heating up incoming gas, preventing it from collapsing into dense structures and forming new stars. This feedback loop not only shapes the rate of star formation but also helps to maintain the balance between the gas supply and the energy budget within a galaxy or cluster. The effects of accretion shocks on star formation are particularly fascinating. In some cases, these shocks can trigger the collapse of gas clouds, leading to the birth of new stars. This phenomenon is often observed in galactic mergers, where shock waves from the interaction between galaxies compress gas clouds, facilitating star formation in what might otherwise be a quiescent region. On the other hand, in more peaceful environments, shocks can prevent star formation by heating up the surrounding gas, making it too hot and diffused to collapse under its own gravity. The complex interplay between shocks and star formation is just one example of how accretion shocks help to regulate the cosmic environment. Another important aspect of this process is their role in the heating of the intracluster medium, ICM. The ICM is the hot, diffuse gas that fills galaxy clusters, and its temperature is crucial in determining the overall dynamics of the cluster. As gas falls into the gravitational well of a cluster, it is subjected to shock waves that heat it to millions of degrees, creating a hot atmosphere around the galaxies. This heating mechanism is essential for maintaining the stability of galaxy clusters and preventing the gas from cooling too quickly. In addition to their impact on galaxy and cluster formation, accretion shocks also have a profound influence on the large-scale structure of the universe. The cosmic web, the vast network of galaxies, clusters, and voids that make up the universe's structure, is shaped by the flow of matter through it. As gas and dark matter accumulate into dense regions, they generate shock waves that influence the distribution of galaxies and clusters. These shock waves can compress and heat the gas in the intergalactic medium, leading to the formation of cosmic filaments, long, thin structures that stretch across vast distances and connect galaxy clusters. Cosmic filaments are some of the largest structures in the universe, and understanding how accretion shocks contribute to their formation is key to understanding the evolution of the cosmic web. These filaments act as the highways through which matter flows, connecting galaxy clusters and facilitating the exchange of energy and material between them. As gas flows along these filaments, it can be compressed and heated by accretion shocks, creating conditions that promote the formation of new galaxies or the growth of existing ones. Moreover, the study of cosmic accretion shocks also offers valuable insights into the nature of dark matter. Dark matter, which makes up about 27% of the universe's mass, interacts only through gravity and the weak nuclear force, making it incredibly difficult to detect directly. However, its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Since accretion shocks play a critical role in the formation of these structures, understanding how they work can help us learn more about the distribution of dark matter in the universe. Shocks can reveal the locations of dark matter concentrations, allowing scientists to map its distribution and better understand its role in the formation of large-scale cosmic structures. In addition to dark matter, another mysterious force at play is dark energy. This invisible force is responsible for the accelerated expansion of the universe, and its effects can be felt across vast cosmic distances. Although dark energy is still not fully understood, researchers are working to uncover how it interacts with the matter and energy in the universe, particularly in relation to accretion shocks. The combination of dark energy's influence on the expansion of the universe and the gravitational effects of accretion shocks creates a dynamic, ever-changing cosmic environment. As we continue to study the way these forces interact, we may be able to uncover new clues about the nature of dark energy and its impact on cosmic evolution. One of the most exciting aspects of accretion shock research is the role of simulations and computational models in advancing our understanding of these phenomena. Thanks to advancements in computing power and numerical techniques, scientists are now able to simulate the behavior of shocks in highly detailed models of the universe. These simulations allow us to test different hypotheses and make predictions about how accretion shocks shape cosmic structures. By comparing the results of these simulations with actual observational data, scientists can refine their understanding of how shocks work and their role in the universe's evolution. Simulations also provide a way to explore the behavior of shocks in environments that are difficult or impossible to study directly. For example, the interactions between black holes, neutron stars, and accretion shocks are extremely complex, and it is challenging to observe these interactions in real time. However, by running detailed simulations, scientists can model the conditions in these extreme environments and gain valuable insights into the behavior of these objects. These simulations are helping to answer some of the most profound questions in astrophysics, such as how black holes grow and how they influence the evolution of galaxies. Moreover, simulations of accretion shocks are also shedding light on the role of magnetic fields in shaping cosmic structures. Magnetic fields are ubiquitous in the universe, and they play a significant role in the dynamics of accretion shocks. When gas flows into a gravitational well, it is often magnetized, and the interaction between the magnetic field and the shock wave can have a profound impact on the behavior of the gas. This interaction can affect the rate of accretion, the temperature of the gas, and the overall structure of the galaxy or cluster. Understanding the role of magnetic fields in these processes is crucial for developing a more complete picture of how accretion shocks shape the universe. As we look ahead, it is clear that the study of cosmic accretion shocks will continue to be a central topic in astrophysical research. With new observational tools, advanced simulations, and growing insights into the nature of dark matter, dark energy, and cosmic evolution, we are on the cusp of uncovering even more profound truths about the universe. The role of accretion shocks in shaping galaxies, clusters, and the cosmic web is just one piece of the puzzle, and as we continue to explore their effects, we will undoubtedly uncover new mysteries and answers that bring us closer to understanding the very fabric of the cosmos. Cosmic accretion shocks are not just fascinating phenomena in their own right. They are essential to the ongoing story of the universe. They are the unseen forces that shape the galaxies and clusters that fill the vastness of space, and they hold the key to understanding the evolution of cosmic structures on the largest scales. From the birth of galaxies to the formation of supermassive black holes, accretion shocks are integral to the forces that govern the cosmos. As we continue to study these cosmic phenomena, we take another step closer to unraveling the deepest mysteries of the universe. As we continue to explore the role of cosmic accretion shocks, it's important to delve deeper into their impacts on smaller-scale cosmic structures. While accretion shocks are often associated with the formation of galaxies and clusters, their effects stretch much further, influencing the formation of star systems, the evolution of the interstellar medium, and the dynamics of individual stars. One of the most intriguing phenomena associated with accretion shocks is their role in the regulation of the interstellar medium, ISM. The ISM is the matter that exists between stars within a galaxy, composed primarily of gas and dust. Understanding how accretion shocks affect the ISM is crucial for understanding the life cycle of galaxies and their ability to sustain star formation over time. Shocks from accretion events can compress the gas within the ISM, causing it to cool and condense into dense clouds, setting the stage for new star formation. In this way, shocks can kickstart star formation in otherwise quiescent regions of a galaxy. However, while shocks can trigger star formation, they can also act as inhibitors. High-energy accretion shocks, especially those produced by the accretion of matter onto supermassive black holes, can release vast amounts of energy in the form of radiation and heat, which can heat up the surrounding gas, preventing it from collapsing into stars. This process, known as feedback, is essential for understanding why some galaxies stop forming stars despite having an ample supply of gas. Essentially, the energy released by accretion shocks can regulate the star formation rate within galaxies, maintaining a balance that prevents excessive star formation in certain regions. The feedback from accretion shocks also plays a key role in the evolution of star clusters. Star clusters are groups of stars that form together from the same molecular cloud. In some cases, the energy released by accretion shocks in the vicinity of these clouds can compress the gas, triggering the formation of new stars. In other situations, the shock waves can disperse the gas, preventing it from condensing into dense clusters. This delicate balance between compression and disruption dictates whether a star cluster can form and grow or whether it will be scattered apart before it can evolve into a stable structure. The dynamics of accretion shocks also extend to the study of black holes, particularly supermassive black holes located at the centers of galaxies. As matter falls toward these black holes, it forms an accretion disk, a spinning disk of gas and dust heated to extremely high temperatures. The energy produced by these accretion disks is immense, often outshining the entire galaxy in terms of luminosity. The shocks produced in the accretion process can emit X-rays, gamma rays, and other forms of high-energy radiation, providing us with one of the most direct ways to observe black holes. These energetic outflows are not only fascinating in terms of their immediate effects on the surrounding environment, but also play a crucial role in the evolution of galaxies. As gas is funneled toward a black hole, it often encounters shock waves that can expel material back into the surrounding space. This feedback mechanism can prevent excessive accretion onto the black hole and regulate the amount of matter feeding it. This process has been hypothesized as a key factor in maintaining the stability of galaxies, as it helps to limit the growth of the black hole and prevent the galaxy from becoming overwhelmed by the energy released during accretion. The relationship between accretion shocks and black holes is also a critical piece of the puzzle when it comes to understanding the formation and evolution of supermassive black holes. Supermassive black holes are thought to reside at the centers of most large galaxies, and their formation is closely tied to the growth of their host galaxies. Accretion shocks are believed to play a significant role in the growth of these supermassive objects. As gas and dust are funneled toward the center of the galaxy, accretion shocks can influence the rate at which material is added to the black hole. The energy released during this process can also affect the surrounding galaxy, contributing to the complex interplay between black holes and their environments. The study of accretion shocks in the context of black hole formation is closely linked to the study of cosmic evolution on a much larger scale. When we observe distant galaxies, we are often looking at snapshots of the universe at different points in time, allowing us to trace the evolution of cosmic structures over billions of years. By studying the role of accretion shocks in these distant galaxies, scientists can learn about the conditions that led to the formation of large-scale structures like galaxy clusters, supermassive black holes, and cosmic filaments. In essence, accretion shocks serve as a cosmic lens, allowing us to peer back in time and understand how the universe evolved from its early stages to the complex structures we observe today. As we continue to develop more advanced observational techniques and computational models, our understanding of the role of cosmic accretion shocks in the universe will continue to evolve. We now have the ability to observe the effects of accretion shocks across a wide range of wavelengths, from radio waves to X-rays, allowing us to study their impact on both large and small scales. With the advent of powerful space telescopes like the James Webb Space Telescope, we will be able to peer deeper into the cosmos than ever before, revealing new insights into the mechanics of accretion and the role of shocks in the formation and evolution of galaxies, clusters, and other cosmic structures. Moreover, the growing field of gravitational wave astronomy promises to offer a new avenue for studying accretion shocks, especially in the context of black hole mergers and other high-energy events. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. By studying the way these waves interact with matter and energy, scientists can gain valuable information about the behavior of shocks in extreme environments. As gravitational wave observatories like LIGO and Virgo continue to make groundbreaking discoveries, they will provide a new perspective on the role of accretion shocks in shaping the universe. Beyond their role in the formation of galaxies and clusters, accretion shocks also play a critical role in the interaction between galaxies. Galactic collisions, which are relatively common in the universe, often result in the formation of shock waves that propagate through the gas and dust of the colliding galaxies. These shocks can compress gas, triggering star formation in what was once a calm and inactive region. The impact of these shocks can also lead to the creation of new structures, such as tidal tails, rings, and even entire new galaxies. By studying these interactions, we can learn more about how galaxies grow and evolve through their collisions and the role that accretion shocks play in this process. Looking even further into the future, accretion shocks may reveal key insights into some of the most fundamental questions in physics. For example, the study of these shocks could help answer questions about the nature of dark energy, which is thought to drive the accelerated expansion of the universe. By understanding how accretion shocks influence the distribution of matter and energy across vast cosmic distances, we may uncover new clues about the forces that are shaping the universe on the largest scales. Similarly, accretion shocks may provide new insights into the nature of dark matter, which remains one of the biggest mysteries in modern astrophysics. Dark matter is believed to make up the majority of the mass in the universe, yet it cannot be detected directly. By studying the effects of accretion shocks on visible matter, scientists may be able to infer the presence of dark matter in regions where it has not yet been observed. This, in turn, could help refine our understanding of the distribution of dark matter and its role in the formation of galaxies and clusters. The study of cosmic accretion shocks is not just about understanding the immediate effects of shock waves on gas and matter. It is about uncovering the fundamental processes that govern the evolution of galaxies, clusters, and the universe as a whole. From the formation of supermassive black holes to the regulation of star formation, accretion shocks are intimately tied to the development of the cosmos. As we continue to refine our observational and computational tools, we are poised to uncover even more profound insights into the nature of the universe, and accretion shocks will undoubtedly remain a central topic in this ongoing journey of discovery. As we continue to peel back the layers of the cosmic accretion shock phenomenon, it becomes clear that these shocks are much more than transient events. They are key drivers in shaping the universe. Their influence extends far beyond the realms of individual galaxies and clusters, influencing the very fabric of the cosmos in ways we are only beginning to comprehend. One area where cosmic accretion shocks have proven to be especially important is in the study of cosmic filaments. These massive, thread-like structures are part of the vast cosmic web that makes up the large-scale structure of the universe. Filaments connect galaxy clusters and superclusters, and they often contain vast quantities of gas, most of which is in the form of hot, diffuse plasma. The gas within these filaments is not static. It is constantly being affected by the accretion of matter, and the shock waves that accompany this process. These shocks can heat the gas to millions of degrees, influencing the overall temperature and density of the filaments. This heated gas plays an essential role in the overall behavior of the cosmic web. It can affect the motion of galaxies and galaxy clusters within the filament, influencing their growth and evolution. The shock waves can also have a significant impact on the dark matter that is believed to be present within these filaments. While dark matter cannot be directly observed, it is thought to exert gravitational influence on the visible matter within galaxies and clusters. By studying the interaction between cosmic accretion shocks and dark matter, scientists may one day uncover the true nature of dark matter and its role in the evolution of the universe. The impact of accretion shocks on cosmic filaments extends to the largest structures in the universe, superclusters. These immense structures are made up of dozens, if not hundreds, of galaxy clusters that are gravitationally bound together. Superclusters are some of the most massive objects in the universe, and they provide a unique laboratory for studying the effects of accretion shocks on a grand scale. The shock waves that propagate through superclusters can influence the motion of galaxies, leading to the formation of even larger-scale structures. Additionally, these shocks can have an impact on the temperature and density of the gas within superclusters, shaping the overall dynamics of these colossal cosmic structures. Another important aspect of cosmic accretion shocks is their role in the growth and evolution of cosmic voids. These vast regions of space, which contain relatively few galaxies or other visible matter, are often thought of as the empty parts of the universe. However, recent studies have shown that even in these voids, cosmic processes such as accretion and shocks can play a significant role. As matter flows into these voids, it can encounter shock waves that heat the gas and influence the behavior of galaxies within the voids. This heating process can affect the formation of galaxies in these regions, altering their properties and preventing them from evolving in the same way as galaxies in more densely populated regions of the universe. Cosmic accretion shocks are also instrumental in the study of galaxy mergers. These mergers, which occur when two or more galaxies collide and combine into a single, larger galaxy, are some of the most dramatic events in the universe. During these collisions, shock waves are produced that can influence the gas and dust within the galaxies, triggering star formation or even disrupting the structures of the merging galaxies. The energy released during these mergers can also affect the surrounding environment, altering the distribution of gas and dark matter in the region. By studying the role of accretion shocks in galaxy mergers, scientists can gain valuable insights into the processes that shape the formation and evolution of galaxies. The study of cosmic accretion shocks also opens the door to understanding some of the most fundamental questions in physics. One of these questions concerns the nature of cosmic inflation, a period of rapid expansion that occurred shortly after the Big Bang. During inflation, the universe expanded exponentially, stretching space-time and creating the large-scale structures we observe today. The shock waves produced during the accretion of matter into galaxies and clusters may provide clues about the conditions that existed during this early phase of the universe's evolution. By studying these shocks, scientists can test theories about inflation and gain a deeper understanding of the forces that shaped the universe from its inception. Furthermore, the role of accretion shocks in galaxy formation and evolution could help answer questions about the fundamental nature of matter and energy. The way in which shock waves interact with gas, dust, and dark matter provides insight into the underlying forces that govern the cosmos. Understanding how these forces work at both large and small scales can shed light on some of the most profound mysteries of physics, from the behavior of dark energy to the unification of the fundamental forces of nature. The study of cosmic accretion shocks is also intrinsically linked to the quest for extraterrestrial life. The conditions that allow life to thrive on Earth are closely tied to the processes that occur within galaxies, including the heating and cooling of gas and the formation of stars and planets. By studying the effects of accretion shocks on star formation, scientists can better understand how stars and planets form, and whether similar conditions might exist elsewhere in the universe. This knowledge is crucial for the search for life beyond Earth, as it helps scientists identify the most promising regions of the cosmos where life could potentially arise. In addition to their role in the formation of stars and planets, cosmic accretion shocks also play a crucial part in the behavior of black holes. As we mentioned earlier, the matter that falls into black holes undergoes a dramatic process of compression and heating. This process is accompanied by the release of vast amounts of energy in the form of radiation, which can have a significant impact on the surrounding environment. The shock waves produced by this energy can influence the motion of nearby gas, triggering the formation of new structures or altering the dynamics of existing ones. The study of these interactions is vital for understanding the behavior of supermassive black holes and their impact on the surrounding galaxies. While we have learned much about cosmic accretion shocks, there is still much to discover. The universe is an incredibly complex and dynamic place, and new observations and discoveries continue to challenge our understanding of the role these shocks play in shaping the cosmos. As technology advances, scientists will be able to observe more distant regions of the universe and gain a more comprehensive understanding of the processes that drive cosmic evolution. In the near future, new telescopes, both ground-based and space-based, will provide unprecedented views of the universe, allowing scientists to probe the effects of accretion shocks in greater detail than ever before. One exciting development on the horizon is the continued advancement of gravitational wave astronomy. Gravitational waves, which were first detected in 2015 by the LIGO Observatory, provide a new way of observing the universe. These ripples in spacetime are caused by the acceleration of massive objects, such as the collision of black holes or neutron stars. The study of these waves promises to provide new insights into the processes that occur during cosmic accretion and the formation of galaxies, clusters, and black holes. As more gravitational wave observatories come online and as detection techniques improve, the study of accretion shocks will only become more refined and more detailed. Cosmic accretion shocks are one of the most fundamental and powerful forces in the universe. From the formation of galaxies to the regulation of star formation, accretion shocks shape the cosmos on every scale. By studying these shocks, we can unlock the secrets of the universe's past, present, and future, gaining insights into the formation and evolution of cosmic structures, the behavior of dark matter and dark energy, and even the nature of life itself. As our understanding of accretion shocks continues to evolve, we are bound to uncover even more profound truths about the universe and our place within it. The beauty of cosmic accretion shocks lies in their far-reaching effects across the cosmos, transforming everything from the smallest of galaxies to the grandest of superclusters. As we continue to investigate these cosmic phenomena, we realize how interconnected the universe truly is. Accretion shocks don't just influence the immediate area they occur in. They ripple across vast distances, shaping the universe's larger structure and influencing the behaviors of matter and energy on a grand scale. Understanding these events is crucial not just for astronomers, but for anyone looking to understand the universe's fundamental workings. The formation of galaxies is one of the most vital aspects where cosmic accretion shocks play a role. In the earliest stages of the universe, right after the Big Bang, matter began to cool and condense, forming the first galaxies. This process didn't happen smoothly. Rather, gravitational forces caused matter to accumulate in clumps, with shock waves playing a significant part in shaping the material that would eventually form stars, galaxies, and even black holes. These shockwaves heated up gas, setting the stage for more complex structures to evolve. The energy from these shocks also helped initiate the formation of the very first stars, igniting a new chapter in the universe's history. We also need to consider the role of cosmic accretion shocks when it comes to the distribution of gas and energy across the universe. As galaxies continue to grow and evolve, accretion of gas into these galaxies is inevitable. The shockwaves that result from the accretion process not only heat up this gas but also shape its overall distribution. For example, when a galaxy merges with another, or when matter flows into a galaxy's core, the shockwaves produced can significantly alter the galaxy's internal structure. It's these shocks that help to drive star formation by pushing the gas and dust into denser regions, making it more likely that new stars will be born. On the larger scale, accretion shocks are crucial in forming galaxy clusters. These are collections of hundreds or thousands of galaxies bound together by gravity. These clusters don't just sit idly in space. They are dynamic and constantly in flux. The shockwaves generated from the accretion of gas into these clusters affect the movement and behavior of galaxies within them. For instance, galaxies within these clusters often experience a phenomenon known as galactic harassment, where the gravitational forces of nearby galaxies cause their orbits to change. This, in turn, can trigger a variety of effects, from starbursts, when a large number of new stars are suddenly born, to the creation of vast, diffuse halos of gas that span across the entire cluster. Additionally, it's crucial to understand that these shockwaves do not just heat gas, they also compress it. This compression can have profound effects on the formation of cosmic structures. When gas is compressed due to shockwaves, it creates the ideal conditions for new stars to form. This process is a key part of galaxy evolution, as it leads to the creation of stellar nurseries, regions of space where new stars are born at a rapid pace. This can significantly alter the shape and structure of a galaxy over time, as the formation of stars can trigger changes in the gravitational forces at play. In some instances, shockwaves may even stop star formation, cooling the gas and preventing it from clumping together in the way that would normally lead to the birth of new stars. However, cosmic accretion shocks aren't only concerned with star formation and galaxy growth. These phenomena also play a significant role in the study of the intergalactic medium. This is the space between galaxies, which contains gas and dust particles. Much of this medium is heated by shockwaves, particularly in regions near galaxy clusters, where the temperatures of the gas can reach millions of degrees. By studying how shockwaves affect the intergalactic medium, scientists can gain valuable insights into the state of the universe during different epochs in its history. For instance, shockwaves can reveal information about the time when the universe transitioned from being opaque to transparent, a key moment in the early history of the cosmos. Cosmic accretion shocks also provide key insights into the behavior of dark matter, the invisible substance that makes up most of the mass in the universe. While we cannot observe dark matter directly, we know of its presence because of its gravitational effects on galaxies and clusters. When shockwaves move through clusters of galaxies, they can affect the distribution of dark matter in ways that provide clues to its nature. For example, by analyzing how the shockwaves alter the behavior of dark matter in galaxy clusters, scientists may be able to uncover the hidden properties of this elusive substance. Another intriguing aspect of cosmic accretion shocks is their influence on the formation of supermassive black holes. These black holes, which sit at the centers of most galaxies, are some of the most mysterious and powerful objects in the universe. As matter falls toward the black hole, it is heated and compressed, generating powerful shockwaves. These shockwaves not only affect the immediate vicinity of the black hole but can also extend outward, influencing the surrounding gas and stars. This process is thought to be a key driver in the growth of supermassive black holes and the formation of active galactic nuclei, regions where the energy emitted by a black hole can outshine the rest of the galaxy combined. One might also ask how cosmic accretion shocks influence the evolution of supernovae. These spectacular explosions occur when massive stars reach the end of their life cycle. During the explosion, shockwaves are produced that send shock fronts out into the surrounding space. These shockwaves are responsible for spreading heavy elements such as carbon, oxygen, and iron throughout the universe, enriching the interstellar medium with the building blocks for new stars and planets. Additionally, supernova shockwaves can trigger the formation of new stars by compressing nearby gas clouds, contributing to the ongoing cycle of birth, death, and rebirth within galaxies. As we consider the ongoing evolution of the universe, We must also take into account the role of cosmic accretion shocks in the interaction between galaxies and the cosmic microwave background, CMB. The CMB is the faint glow left over from the Big Bang, and it provides a snapshot of the early universe. As shockwaves move through the universe, they can distort the CMB, creating small ripples or patterns that can be observed by telescopes. These distortions provide valuable clues about the processes that occurred in the early universe, including the nature of the first stars and galaxies. What's truly exciting is how cosmic accretion shocks are paving the way for more groundbreaking discoveries about the universe's evolution. New technologies, like more powerful space telescopes and increasingly sophisticated computational simulations, are allowing scientists to examine these shocks in greater detail than ever before. As these tools continue to improve, our understanding of how shockwaves shape the universe will become increasingly refined, revealing the hidden mechanisms that govern cosmic structures. It is through this lens that we are beginning to unravel the mysteries of the universe, mysteries that were once hidden deep within the cosmic void, waiting to be discovered. In the coming years, as we continue to push the boundaries of our observational capabilities, we can expect even more profound discoveries about cosmic accretion shocks and their role in the universe's ongoing evolution. Whether it's unraveling the mysteries of dark matter, understanding the complex interactions between galaxies and black holes, or discovering new cosmic phenomena, the study of cosmic shocks promises to provide us with answers to some of the most profound questions about the universe's origins, structure, and future. With the ability to study cosmic accretion shocks in greater detail, we are set to explore new frontiers in astrophysics, offering us a clearer picture of how the universe operates on the largest scales. As this research unfolds, we may find ourselves closer to answering one of the most profound questions of all: how did the universe, from its chaotic and violent origins, become the vast, structured cosmos we see today? As we continue to explore the impact of cosmic accretion shocks, it's important to dive deeper into how they influence the formation of large-scale structures in the universe. The universe, as vast and intricate as it is, operates on many levels, from the smallest particles to the largest galaxies and galaxy clusters. Cosmic accretion shocks play a significant role in shaping this vast landscape, influencing how galaxies form, interact, and evolve over billions of years. The shockwaves generated during galaxy and cluster formation are not merely side effects of cosmic processes. They are central to how the structure of the universe itself is shaped. One of the most significant effects of cosmic accretion shocks can be seen in the formation of the cosmic web. This web-like structure, made up of vast filaments of galaxies, dark matter, and gas, stretches across the universe, connecting galaxies and clusters in a grand cosmic network. It is the very backbone of the universe. The formation of this web is largely driven by gravitational forces, but shockwaves from accreting matter help shape its structure in profound ways. These shockwaves compress and heat the gas in the filaments, influencing how the galaxies within them move and evolve. This has a cascading effect, shaping the larger cosmic structures and defining the gravitational interactions that occur between them. The cosmic web is not a static structure. It is constantly evolving, with galaxies and clusters of galaxies moving along the filaments and interacting with one another. Cosmic accretion shocks are instrumental in this evolution, as they help regulate the flow of gas and matter through the cosmic web. These shockwaves, in a sense, dictate the pace of cosmic evolution, pushing matter together, creating dense pockets of gas and stars, and triggering the formation of new galaxies. Without these shocks, the large-scale structures of the universe would look vastly different, more disorganized and fragmented, lacking the defined patterns that we see today. In addition to their role in shaping large-scale structures, cosmic accretion shocks also play a crucial part in the heating and ionization of gas across the universe. The gas in the universe is not static. It is constantly moving, interacting with itself and with other forms of matter. As matter accretes into galaxies or clusters, shockwaves heat the gas to incredibly high temperatures. This process ionizes the gas, stripping atoms of their electrons and creating a hot, diffuse plasma. The energy released by these shocks can be immense, sometimes reaching millions of degrees Celsius. This ionization process is crucial for the evolution of the universe, as it helps create the conditions for star formation and other key processes in cosmic evolution. The heating of gas by accretion shocks is not just a local phenomenon, it has far-reaching consequences for the overall state of the universe. When gas is heated to such extreme temperatures, it becomes less dense and more diffuse. This, in turn, affects the way galaxies form and evolve. For example, the hot gas generated by accretion shocks can prevent new gas from cooling and condensing to form stars, effectively halting star formation in certain regions. On the other hand, in regions where the gas is able to cool and condense, shockwaves can help trigger the birth of new stars, contributing to the ongoing cycle of star formation and death in galaxies. Another fascinating aspect of cosmic accretion shocks is their role in driving the activity of supermassive black holes. At the centers of most large galaxies lies a supermassive black hole, whose gravitational pull is so intense that it influences the entire galaxy. As matter falls toward these black holes, it is heated to extreme temperatures, creating powerful shockwaves that can have far-reaching effects on the surrounding galaxy. These shockwaves can heat the gas around the black hole, preventing it from cooling and forming new stars. In some cases, the energy released by these shockwaves can even drive large-scale outflows of gas, known as active galactic nuclei, AGN, jets, which are capable of reaching out across entire galaxies, influencing their evolution. Supermassive black holes and their associated shockwaves also play a significant role in regulating the growth of galaxies. As matter falls into the black hole and is heated by the accretion process, the energy released can prevent further matter from accreting, effectively halting the growth of the galaxy. This process is thought to be a key mechanism behind the formation of the so-called red and dead galaxies, which are galaxies that have exhausted their supply of star-forming material. The feedback loops created by these accretion shocks are essential in controlling the growth and evolution of galaxies, ensuring that they do not grow too large or too quickly. In terms of large-scale cosmic evolution, cosmic accretion shocks are also thought to be responsible for the phenomena we observe in galaxy clusters. These clusters are massive structures, often containing hundreds or even thousands of galaxies bound together by gravity. The gas that fills these clusters is not static. It is constantly being heated and influenced by shockwaves. These shockwaves shape the distribution of gas in the cluster, affecting the movement of galaxies within it. The shockwaves can also trigger the formation of new stars and the creation of new structures within the cluster. For example, some galaxy clusters contain vast, diffuse clouds of gas that are heated by shockwaves, leading to the formation of new stars and galaxies. The feedback loops created by cosmic accretion shocks are crucial in determining the long-term evolution of galaxy clusters. These feedback mechanisms regulate the flow of gas and energy within the clusters, helping to maintain a balance between star formation, gas heating, and galaxy growth. Without these shocks, galaxy clusters could become overrun with gas and stars, leading to an overly dense and chaotic environment. Instead, the shockwaves act as a sort of cosmic thermostat, regulating the temperature and density of gas within the cluster and ensuring that the structure remains stable over time. As we look to the future, it's clear that the study of cosmic accretion shocks will continue to yield new insights into the workings of the universe. With advancements in observational techniques and computational simulations, scientists are gaining a deeper understanding of how these shocks operate on both small and large scales. The study of cosmic shocks has already led to groundbreaking discoveries about the nature of dark matter, the evolution of galaxies, and the behavior of supermassive black holes. As our ability to observe the universe improves, we will undoubtedly uncover even more mysteries about these enigmatic forces and their role in shaping the cosmos. Cosmic accretion shocks are a vital part of the universe's evolution. They play a crucial role in shaping the structure of galaxies, clusters, and the larger cosmic web. They heat gas, trigger star formation, regulate galaxy growth, and influence the behavior of supermassive black holes. The energy and matter unleashed by these shocks are key drivers of cosmic evolution, dictating the pace of change in the universe. Understanding the mechanisms behind these shocks is essential for unraveling the mysteries of the cosmos, offering us a deeper insight into the nature of the universe and our place within it. As we continue to delve deeper into the role of cosmic accretion shocks, it's essential to examine their intricate relationship with the underlying forces that govern the cosmos. While the heating and shaping of gas through these shocks is crucial to understanding cosmic evolution, these shocks also interact with dark matter, one of the most mysterious and elusive substances in the universe. Dark matter, which makes up roughly 27% of the universe's total mass energy content, does not emit, absorb, or reflect light, making it invisible to our current observational tools. Yet, its gravitational effects are unmistakable, shaping the formation of galaxies and clusters and influencing the distribution of matter across vast cosmic scales. The relationship between dark matter and cosmic accretion shocks is complex and still a subject of active research. Accretion shocks help shape the large-scale structure of the universe, and in doing so, they also influence the distribution and behavior of dark matter. In galaxy clusters, for instance, the distribution of dark matter can be traced by observing the behavior of the gas surrounding it. When gas is compressed and heated by shockwaves, it can reveal the presence of dark matter through gravitational lensing, a phenomenon in which light from distant objects is bent by the gravitational field of a massive object, like a galaxy cluster, creating a distorted image. This process is one of the primary ways astronomers can infer the presence and distribution of dark matter in the universe. Furthermore, the presence of shockwaves in the intergalactic medium, the vast expanse of gas between galaxies, plays a role in the way dark matter interacts with visible matter. As shockwaves propagate through the intergalactic space, they may influence the way dark matter behaves within the gravitational fields of galaxy clusters. Some theories suggest that these shocks could affect the distribution of dark matter within clusters, leading to differences in how galaxies are formed or how they evolve over time. While much is still unknown about the specifics of these interactions, it's clear that cosmic accretion shocks and dark matter are inextricably linked, and understanding this relationship is vital to understanding the full scope of cosmic evolution. At the heart of these processes is gravity, the fundamental force that binds the universe together. Gravity drives the formation of galaxies, clusters, and even larger-scale structures like superclusters and voids. It is also responsible for the formation of shockwaves during the process of accretion, as matter falls toward the center of galaxies or clusters, creating high-energy collisions. The gravitational pull exerted by massive objects, like galaxies and clusters, leads to the accumulation of gas and dust, which then undergoes violent shocks as they are drawn together. These shocks not only heat the gas to extreme temperatures but also contribute to the overall gravitational dynamics of the system. The result is a delicate balance between matter, gas, dark matter, and the gravitational forces that govern their motion, with accretion shocks playing a central role in maintaining this balance. One of the most striking features of cosmic accretion shocks is the energy they release. These shocks can generate energy on an unimaginable scale, often surpassing the energy produced by entire galaxies. The heating of gas during the accretion process can result in temperatures that exceed tens of millions of degrees Celsius. This intense heat produces a phenomenon known as X-ray emission, which can be observed by space-based telescopes. The X-ray emissions from these shock-heated gases provide valuable insights into the underlying processes driving the shocks. By studying these emissions, scientists can gain a deeper understanding of the conditions that prevail in galaxy clusters, including the density and temperature of the gas and the influence of dark matter. The study of X-rays from shock-heated gas has already led to numerous discoveries, including new insights into the behavior of galaxy clusters. For example, astronomers have observed that the temperature of the gas within clusters increases dramatically in the regions where accretion shocks are most intense. This heating of gas provides clues about the rate at which matter is being accreted into the cluster, and the overall growth of the cluster itself. By tracking the X-ray emissions from these regions, scientists can build detailed models of how shockwaves propagate through the gas, allowing them to predict the evolution of clusters over time. In addition to the X-ray emissions, cosmic accretion shocks can also generate other forms of radiation, including radio waves. These radio emissions are typically associated with the acceleration of charged particles, which are pushed to high velocities by the shockwaves. The resulting synchrotron radiation, emitted when charged particles spiral through magnetic fields, can be detected by radio telescopes, offering another window into the processes taking place during accretion. The study of these radio emissions has revealed fascinating details about the behavior of galaxies and clusters, including the presence of magnetic fields and the acceleration of cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. The role of magnetic fields in cosmic accretion shocks is another area of active research. Magnetic fields are present throughout the universe, including in galaxies, clusters, and even the intergalactic medium. These fields play a crucial role in the behavior of charged particles, as they can accelerate particles to high velocities and influence the way shockwaves propagate through the gas. Magnetic fields can also help channel the energy from accretion shocks, focusing it into certain regions of the cluster or galaxy. This can lead to the formation of powerful jets or outflows of gas, which can have a significant impact on the surrounding environment. The interaction between magnetic fields and shockwaves is a complex process, and understanding how these fields influence cosmic evolution is a key focus of current research in astrophysics. As we continue to explore the implications of cosmic accretion shocks, it becomes clear that these phenomena are not isolated events. They are part of a broader process of cosmic evolution that encompasses the birth, growth, and eventual death of galaxies and clusters. The shockwaves generated during accretion play a pivotal role in shaping the dynamics of these objects, influencing everything from the rate of star formation to the distribution of dark matter and gas. Moreover, they contribute to the overall structure of the universe, dictating how galaxies and clusters form, evolve, and interact with one another. Despite the remarkable progress that has been made in understanding cosmic accretion shocks, much remains unknown. The processes behind these shocks are still not fully understood, and scientists are only beginning to scratch the surface of how they influence the larger-scale structure of the universe. As technology advances and new observational tools are developed, we can expect even more breakthroughs in our understanding of these cosmic phenomena. The study of cosmic accretion shocks is not just about understanding how galaxies and clusters form. It is about understanding the very forces that shape the universe itself. The role of cosmic accretion shocks is far-reaching and multifaceted. They are not merely side effects of galaxy formation or byproducts of gravitational collapse. They are central to the processes that govern the universe's evolution. From shaping the cosmic web to influencing the behavior of supermassive black holes and dark matter, these shocks play a vital role in the ongoing story of the cosmos. As we continue to uncover the mysteries of these powerful forces, we move closer to understanding the fundamental workings of the universe itself and our place within it. As we continue our exploration of cosmic accretion shocks, it's important to consider the broader implications of these events on the overall cosmic landscape. The dynamics of accretion and shock heating are not only pivotal for galaxy and cluster formation but also for the larger cosmic evolution. Over time, as gas, dark matter, and energy collide, they give birth to some of the most magnificent and enigmatic features in the universe. One of the crucial outcomes of cosmic accretion shocks is their impact on the formation of supermassive black holes. These mysterious and often elusive objects lie at the center of most galaxies and clusters, wielding an immense gravitational influence. The process of accretion, especially in regions with intense shockwaves, is believed to play a significant role in fueling the growth of these black holes. As matter falls into a galaxy or cluster, it can be drawn toward the central supermassive black hole, forming an accretion disk around it. The intense heat and energy produced by shockwaves in the surrounding gas can contribute to the acceleration of matter within this disk, enabling the black hole to grow even further. But the role of cosmic accretion shocks doesn't stop there. These shockwaves also contribute to the phenomena known as active galactic nuclei, AGN. AGNs are extremely luminous regions found at the centers of some galaxies, often powered by the activity of a supermassive black hole. When shockwaves from accretion or other energetic processes collide with the gas around an AGN, they can cause a massive release of energy, producing light across a wide range of wavelengths, from radio waves to gamma rays. The interaction between shockwaves and the environment of the AGN can provide astronomers with valuable insights into the nature of these incredibly energetic phenomena. It may also offer a glimpse into the early universe, where the formation of galaxies and supermassive black holes was taking place at an accelerated rate. To understand the full scope of cosmic accretion shocks, we need to broaden our view to the grander cosmic scale. These shockwaves are not isolated events confined to specific galaxies or clusters. Instead, they are an essential part of the processes that shape the cosmic web, a vast network of galaxies, gas, and dark matter that stretches across the universe. The cosmic web itself is formed by the gravitational attraction between matter, which causes galaxies to cluster together, forming enormous filaments and voids. These structures are the result of cosmic accretion, which pulls matter together over billions of years. Accretion shocks play a vital role in the formation and evolution of the cosmic web. As gas and dark matter accumulate along these cosmic filaments, shockwaves are generated, heating the gas and influencing the formation of galaxies. These shockwaves help define the density and temperature distributions of gas across the cosmic web, influencing everything from the rate of star formation to the interactions between galaxies. Without these shocks, the cosmic web would not have the same structure, and the evolution of galaxies and clusters would be very different. Moreover, the shocks generated during the process of accretion contribute to a phenomenon known as cosmic feedback. This refers to the way energy and matter from supermassive black holes, stars, and galaxies can influence their surroundings, creating a feedback loop that affects the evolution of the entire system. In the context of cosmic accretion shocks, feedback can occur in various ways. For example, when shockwaves heat the gas around a galaxy or cluster, they can prevent further accretion of gas, effectively shutting off star formation. This is particularly evident in the case of galaxy clusters, where the gas is often so hot that it cannot collapse further to form stars. The feedback process plays a critical role in regulating the growth of galaxies and clusters, and it helps maintain a balance between the creation of new stars and the preservation of existing structures. The interplay between accretion shocks and cosmic feedback is a subject of intense study, as scientists strive to understand how these processes shape the universe's evolution. One of the key challenges in this area is deciphering the complex interactions between gas, dark matter, and radiation in the presence of shockwaves. As more data is collected through advanced telescopes and simulations, researchers are gaining new insights into how cosmic feedback operates and its effects on the large-scale structure of the universe. As we look deeper into the role of accretion shocks, it's important to remember that the universe itself is constantly evolving. The shocks that we observe today are the result of billions of years of cosmic history, and they provide a glimpse into the forces that have shaped the universe from its very beginning. Every galaxy, every cluster, and every shockwave is part of an ongoing story of cosmic evolution, with each piece of the puzzle offering new clues about the fundamental nature of the cosmos. One fascinating aspect of these shocks is their ability to reveal the history of the universe itself. The study of shock-heated gas and its properties can provide us with valuable information about the conditions that existed in the early universe, long before galaxies or even stars had formed. By analyzing the shockwaves in galaxy clusters and other cosmic structures, scientists can gain insights into the formation of large-scale structures, the role of dark matter, and the processes that led to the birth of galaxies. This is one of the reasons why the study of cosmic accretion shocks is so crucial for understanding the universe's past and its future. One of the most significant implications of cosmic accretion shocks is their potential to explain the large-scale structure of the universe. When we look at the distribution of galaxies and clusters, it's clear that the universe is not randomly arranged. Instead, it exhibits a highly structured pattern, with galaxies forming clusters and superclusters that are connected by vast cosmic filaments. This structure, known as the cosmic web, is thought to have formed through the process of accretion. As gas and dark matter accumulate along these filaments, shockwaves are generated, and the matter is compressed and heated. This results in the formation of galaxies and clusters, with the shockwaves influencing their size, shape, and distribution. The cosmic web is not a static structure but one that is constantly evolving, with accretion shocks playing a critical role in this ongoing process. Through the study of cosmic accretion shocks, we can gain a deeper understanding of how the universe's structure has evolved over time. By analyzing the shock-heated gas in galaxy clusters, astronomers can trace the evolution of large-scale structures, shedding light on the processes that shape the cosmos from its early stages to the present day. These insights not only help us understand the history of the universe but also provide valuable information about its future, offering clues about how galaxies and clusters will continue to evolve in the coming billions of years. The study of cosmic accretion shocks also opens the door to understanding some of the most intriguing phenomena in the universe. From supermassive black holes to active galactic nuclei, from cosmic feedback to the mysteries of dark matter, these shocks are at the heart of many of the most significant and exciting discoveries in astrophysics. The insights gained from studying these shocks have the potential to revolutionize our understanding of the cosmos, providing answers to some of the most profound questions about the universe's nature, origin, and destiny. Cosmic accretion shocks are far more than just a secondary feature of galaxy and cluster formation. They are fundamental processes that play a central role in shaping the large-scale structure of the universe. Through their impact on gas, dark matter, and galaxies, these shocks are responsible for much of the cosmic evolution we observe today. By studying these shocks, scientists are uncovering the deep mysteries of the universe, revealing the intricate interactions that govern the cosmos and offering new insights into the forces that have shaped the universe since its inception. As we continue to explore the role of cosmic accretion shocks, we move closer to unraveling the fundamental processes that define the universe itself. As we continue our deep dive into cosmic accretion shocks, it's essential to recognize how these events influence not only galaxy and cluster formation but also play a significant role in the development of large-scale cosmic structures that stretch across the universe. Shocks during accretion processes are not just bystanders in the cosmic dance. They are dynamic forces that drive much of the action in the universe's ongoing evolution. A critical aspect of cosmic accretion shocks is their contribution to what is known as the hot gas in galaxy clusters. This is a key factor in understanding the energy dynamics within these structures. When gas flows into a galaxy cluster, it is compressed and heated to incredibly high temperatures due to the shockwaves produced by accretion. These shockwaves can elevate the gas temperature to tens of millions of degrees, creating a highly energetic environment. This hot gas, often referred to as the intracluster medium, ICM, is a critical component of galaxy clusters. It holds the majority of the visible mass in clusters and plays a key role in how clusters evolve. One of the key questions that arise from this is how the energy from these shocks influences galaxy formation within the cluster. The interaction between shockwaves and the gas is not simply a one-way process. While shockwaves heat the gas also influences the behavior of the shock itself. This creates a dynamic feedback loop where the gas, under the influence of shockwaves, can either promote or suppress the formation of new stars. This process is fundamental to understanding why some galaxy clusters are rich in stars while others appear to be nearly devoid of star formation. The combination of shock heating and gas dynamics can act as a regulator for star formation, creating environments where new stars are either born in abundance or are suppressed due to the heat from shockwaves. This feedback mechanism can also help explain why some galaxy clusters are observed to be in a state of passive evolution. In passive clusters, star formation has slowed down or stopped altogether. The heating of the gas through shockwaves can prevent further gas from cooling and collapsing to form new stars. This has significant implications for the future of galaxy clusters, suggesting that as time progresses, certain clusters may exhaust their star-forming potential, transitioning to an aging state with fewer young stars and a higher proportion of older stars. Conversely, in clusters where shock heating is less significant or where gas cooling is still able to occur, star formation can continue for longer periods, leading to more dynamic and evolving clusters. The study of these phenomena not only sheds light on the evolution of individual galaxy clusters but also has broader implications for understanding the universe at large. The balance between gas cooling and shock heating can provide valuable clues about the ultimate fate of galaxies, clusters, and even the entire cosmic web. Are we witnessing the slow death of star formation in some regions of the universe, or is this merely a temporary phase before new bursts of activity emerge? These questions continue to drive much of the research into cosmic accretion shocks and their role in shaping the cosmos. Another fascinating aspect of accretion shocks is their relationship with dark matter, the mysterious substance that makes up a large portion of the universe's mass but does not emit or interact with light in any detectable way. While dark matter is elusive, its gravitational effects are evident, and it plays a significant role in the formation of large-scale cosmic structures. Accretion shocks are believed to interact with dark matter in complex ways, influencing the distribution of matter in galaxy clusters and beyond. The gravitational pull of dark matter helps to shape the structures that we observe, guiding the flow of gas and matter through the cosmic web. In regions where dark matter is abundant, the effects of cosmic accretion shocks can be amplified, leading to more significant heating of gas and more dynamic interactions within the cluster. This interplay between dark matter and cosmic shockwaves is still an area of active research, with scientists seeking to understand how dark matter might be influencing the processes of galaxy and cluster formation at a deeper level. Some researchers have even hypothesized that the shockwaves generated by the collapse of dark matter halos could play a role in the formation of supermassive black holes at the centers of galaxies. The energy produced by cosmic accretion shocks is also important in understanding the large-scale behavior of the universe itself. The process of accretion can help to redistribute energy throughout cosmic structures, influencing the temperature and density of gas across vast regions. This redistribution of energy can have profound effects on the way that galaxies interact with each other, with shockwaves serving as a primary mechanism for driving these interactions. In regions where galaxies are in close proximity, shockwaves can trigger the process of galaxy merging, a crucial event in the growth and evolution of galaxies. These mergers often result in the formation of larger, more complex structures and can dramatically alter the trajectory of galaxy evolution. The interplay between galaxy mergers and cosmic accretion shocks is an area of particular interest to astronomers and astrophysicists. When two galaxies collide, the shockwaves from the merger can cause a cascade of effects, from the triggering of star formation to the disruption of galactic structures. These mergers can also fuel the growth of supermassive black holes at the centers of galaxies, as the inflow of gas during a merger can provide the necessary material for accretion. As these black holes grow, they can exert a powerful influence on their surroundings, generating high-energy radiation and possibly even altering the dynamics of the entire galaxy. The study of cosmic accretion shocks is also providing new insights into the early history of the universe. By looking at the gas and structures that existed shortly after the Big Bang, scientists can gain a better understanding of how the first galaxies and clusters formed. In the early universe, the first shockwaves were generated as matter began to clump together under the influence of gravity. These shocks played a crucial role in the formation of the first stars and galaxies, and studying them can help us trace the origins of the cosmic structures that we see today. The formation of the first stars is an especially intriguing aspect of cosmic evolution. The shockwaves that occur during accretion processes can compress gas and trigger the collapse of regions of higher density, eventually leading to the birth of stars. These stars, in turn, began to form the building blocks for galaxies, clusters, and larger cosmic structures. Understanding the role of shocks in the formation of these early stars can help us learn more about the conditions that led to the formation of the first galaxies and the subsequent evolution of the universe. As we look further back in time, it becomes evident that cosmic accretion shocks played a crucial role in the formation of the large-scale structures we observe today. Without these shocks, galaxies and clusters would have had a much more difficult time forming and evolving. The energy from accretion shocks helped to shape the distribution of gas and matter, guiding the development of the cosmic web and influencing the growth of galaxies, black holes, and stars. The interaction between shockwaves, gas, and dark matter is a fundamental aspect of the universe's evolution, and it continues to be a key area of research. The role of cosmic accretion shocks in the formation and evolution of galaxies, clusters, and cosmic structures is a crucial piece of the cosmic puzzle. These shocks not only shape the evolution of individual galaxies and clusters but also contribute to the larger-scale structure of the universe. As our understanding of these processes continues to deepen, we are gaining new insights into the fundamental forces that govern the universe's growth and evolution. By studying the interactions between shockwaves, gas, dark matter, and radiation, we are uncovering the secrets of the cosmos and moving closer to understanding the origins and ultimate fate of the universe itself. As we continue to explore the cosmic forces at play, it's important to focus not only on the immediate effects of cosmic accretion shocks but also on the long-term implications they have for the evolution of the universe. The concept of cosmic accretion goes hand in hand with large-scale structure formation, and by understanding the dynamics of these events, we can also uncover more about the ultimate fate of galaxies and galaxy clusters, their interactions, and the progression of cosmic evolution on a much larger scale. The process of cosmic accretion plays a key role in the distribution of galaxies across the universe. The universe is not randomly distributed. Instead, galaxies are grouped together in vast, sprawling clusters, and these clusters are connected by a network of cosmic filaments. These filaments form part of what is known as the cosmic web, a large-scale structure that looks much like a network of threads, with galaxies and clusters forming the nodes of the structure. Understanding the shockwaves that occur during the process of accretion can help explain how these massive filaments formed, how they interact with one another, and why the universe has its current structure. At the heart of these large-scale interactions, cosmic accretion shocks play a fundamental role in sculpting the cosmic web. During the formation of these structures, gravity pulls matter together, creating dense regions where galaxies and clusters form. As this matter collapses, shockwaves are generated, which can have far-reaching effects on the surrounding gas and cosmic material. These shocks can stretch across enormous distances, carrying energy from one part of the cosmic web to another, facilitating the transfer of energy and momentum across vast swathes of the universe. The hot gas heated by accretion shocks plays a major role in how galaxies interact with each other, as well. When galaxies within the same cluster collide or pass near each other, the shockwaves from these interactions can have dramatic effects on their gas content. The resulting pressure and heat can trigger bursts of star formation or suppress it entirely, depending on the nature of the shockwave and the conditions of the gas involved. This process is crucial in determining the evolutionary paths of galaxies. Some galaxies are rejuvenated by shock-induced star formation, while others are starved of gas, leading to a slow decline in activity. The phenomenon of galaxy mergers is one of the most striking manifestations of the effects of cosmic accretion shocks. When two galaxies collide, they can produce shockwaves so intense that they reshape the galaxies entirely. These mergers can lead to the formation of elliptical galaxies, which have smooth, featureless structures as opposed to the disk-like forms of spiral galaxies. The shockwaves generated during the merger event can also lead to the formation of supermassive black holes, which lie at the centers of most galaxies. In fact, some of the most massive black holes are thought to have formed during these violent cosmic collisions, where vast amounts of gas are funneled toward the center of the galaxy, providing the necessary fuel for the black hole to grow. The role of supermassive black holes in the evolution of galaxies cannot be overstated. As these black holes grow, they release vast amounts of energy in the form of radiation, which can influence the surrounding gas and inhibit or encourage star formation, depending on the circumstances. The shockwaves generated by these energetic outflows can further disrupt the gas within the galaxy, leading to a kind of feedback loop. This interaction between galaxies, their central black holes, and the surrounding gas is one of the most complex and fascinating aspects of cosmic evolution. In addition to the interactions within galaxy clusters, accretion shocks can also play a role in the larger-scale dynamics of the universe. One of the key questions in cosmology is how the universe went from the uniform, hot, and dense state of the Big Bang to the complex structures we observe today. Accretion shocks are believed to have been a significant driving force in this transition. As the universe expanded and cooled, matter began to collapse under its own gravity, forming the first stars and galaxies. This process of matter collapse generated shockwaves that helped to shape the early universe, initiating the formation of the first large-scale structures. These early shockwaves were not just localized events, they had a profound impact on the distribution of matter across the entire universe. The energy carried by these shockwaves helped to fuel the formation of the cosmic web, guiding the distribution of galaxies and clusters across vast distances. In fact, the distribution of galaxies in the universe is not uniform. Instead, galaxies tend to cluster together in certain regions, forming dense areas surrounded by vast voids. The cosmic web, with its interconnected filaments, provides a framework for understanding this pattern of distribution. The study of accretion shocks also opens up interesting avenues for understanding the evolution of the universe's energy content. The energy released by these shocks has important consequences for the temperature and density of gas in different regions of the universe. This can, in turn, influence the cooling processes that occur in galaxy clusters and other cosmic structures. The cooling of gas is a key factor in the formation of stars, and by studying the way shockwaves affect gas cooling, we can better understand how star formation rates have changed over time. In some regions, the cooling of gas may be inhibited by shockwaves, leading to a slowdown in star formation, while in other regions, gas cooling may proceed more efficiently, leading to bursts of new star formation. Moreover, shockwaves play a crucial role in the creation of cosmic magnetic fields. As gas and plasma are compressed during an accretion shock, they can generate powerful magnetic fields. These fields can then influence the behavior of the surrounding material, shaping the dynamics of the gas and even influencing the motion of galaxies themselves. Magnetic fields are a fundamental aspect of many astrophysical processes, and understanding how they arise from cosmic shocks is essential for a complete picture of the evolution of cosmic structures. The role of cosmic accretion shocks extends beyond just the formation and evolution of galaxies and clusters. These shocks have a broader impact on the universe's overall behavior, influencing everything from the distribution of matter to the way that galaxies interact with one another. The energy released by these shocks plays a significant role in shaping the cosmic landscape, helping to define the large-scale structures that dominate the universe. As we continue to study these phenomena, we gain new insights into the processes that drive the evolution of the cosmos and the fundamental forces that shape our universe. One of the most exciting aspects of studying cosmic accretion shocks is that they are observable, allowing us to directly investigate these phenomena. Advances in observational techniques have enabled scientists to detect the signatures of accretion shocks in distant galaxy clusters, providing valuable data that can be used to test our models of cosmic structure formation. Instruments like the Chandra X-ray Observatory and the Planck satellite have provided detailed observations of the hot gas and galaxy clusters, allowing scientists to study the effects of shocks on the surrounding material. These observations are key to advancing our understanding of the processes that govern the universe's evolution. By examining the shock signatures in galaxy clusters and comparing them with theoretical models, researchers are refining their understanding of how cosmic structures form and evolve. These studies are not just about understanding the present-day universe but also about unlocking the mysteries of the past. By looking back at the early universe, scientists can gain insights into the conditions that led to the formation of the first galaxies and stars. The role of cosmic accretion shocks in these early processes is critical to understanding the origins of the universe and the complex structures we see today. Cosmic accretion shocks are a fundamental aspect of the universe's evolution. They are central to the formation and shaping of galaxies, clusters, and large-scale structures, influencing everything from the formation of stars to the growth of supermassive black holes. The energy released by these shocks plays a key role in the dynamics of gas and matter, guiding the evolution of cosmic structures. Through the study of these shock waves, we are not only learning more about the present state of the universe but also uncovering the secrets of its past, shedding light on the processes that have shaped the cosmos from its earliest moments to the present day. As we delve further into the ongoing impact of cosmic accretion shocks, we begin to appreciate their role in the universe's larger-scale processes. The forces that shape galaxies and galaxy clusters through shockwaves don't just influence the physical structure of the universe, but also its energetic landscape. These shock events are responsible for a tremendous exchange of energy, contributing to some of the most dynamic phenomena observed in astrophysical contexts. They impact the rate of star formation, regulate the behavior of black holes, and even alter the temperature of vast clouds of gas that permeate galaxy clusters. The energy imparted by these shocks can trigger the acceleration of particles, creating high-energy cosmic rays that travel across the universe. When matter falls into a black hole, it heats up significantly due to immense gravitational forces, and this process is often accompanied by shockwaves. These shocks not only heat the surrounding gas to millions of degrees but also accelerate particles to nearly the speed of light. These high-energy particles can escape the galaxy cluster and travel vast distances, contributing to the cosmic ray background that fills the universe. On a much larger scale, cosmic accretion shocks are also involved in the formation of the first galaxies and structures during the era of cosmic reionization, roughly 1 billion years after the Big Bang. During this period, the universe transitioned from a hot, opaque state into the more transparent, cooler state we observe today. Accretion shocks in this early universe were key to shaping the first large-scale structures and enabling the formation of the earliest galaxies. These shockwaves would have contributed to the distribution of gas and matter, eventually allowing the gravitational collapse that formed the first galaxies. As the universe evolved, these shockwaves continued to shape the cosmic structures we observe today. The collapse of gas clouds within dark matter halos, triggered by gravitational forces, leads to the formation of galaxy clusters and superclusters. The shocks that occur as matter collapses inward can heat the gas to temperatures far higher than those observed in isolated regions. In many ways, this high-energy process serves as the engine for the growth and evolution of large-scale structures. It is a process driven by fundamental forces of gravity and thermodynamics, constantly pushing matter into ever more complex configurations. As these shockwaves propagate across galaxy clusters, they also have a profound effect on the magnetic fields in these regions. Magnetic fields in the universe are not static but are shaped and amplified by shocks. The gas in galaxy clusters is predominantly composed of ionized particles, plasma, which reacts strongly to magnetic fields. When shocks pass through these regions, the magnetic fields are compressed, stretched, and twisted, producing what are known as magnetic field knots, or turbulent magnetic structures. These fields are not only a product of the shocks but also play a crucial role in the dynamics of the plasma within clusters. They influence the behavior of cosmic rays, regulate particle motion, and can even affect the way that matter moves across the entire cluster. The study of cosmic shocks is deeply intertwined with the study of cosmic magnetism. While magnetic fields in the universe are often weak by terrestrial standards, they play an outsized role in the behavior of cosmic plasmas. Shock-generated magnetic fields can lead to the creation of large-scale cosmic jets, visible in active galactic nuclei, AGN, or the regions surrounding black holes. These jets of energetic particles are driven by the intense shockwaves and the electromagnetic forces within the magnetic fields. Understanding these fields and their interaction with the shocks provides a critical window into the most energetic processes in the universe. One of the exciting aspects of cosmic accretion shocks is that they are not just a one-time event in the universe's history. These shocks are an ongoing process, affecting galaxies, clusters, and other cosmic structures across cosmic timescales. The energy from these shockwaves is continuously transferred and reshaped as it moves through the universe. For instance, in the case of the interaction between galaxy clusters, where one cluster collides with another, shocks can reignite star formation in some regions or completely halt it in others. The effects of these shocks extend far beyond the region of their origin and can impact the larger-scale dynamics of the galaxy cluster. The process of shock-induced star formation, as mentioned earlier, can lead to bursts of activity within galaxies. When a shockwave compresses the gas within a galaxy, it can trigger the conditions necessary for stars to form. This is especially evident in the case of galaxy mergers, where the intense interactions between galaxies often spark a flurry of star formation. On the flip side, shockwaves can also heat up the gas to such an extent that star formation is suppressed, creating an environment where galaxies become quenched and no longer produce new stars. This complex interplay between shock-induced heating and cooling is a vital factor in determining the evolution of galaxies and their eventual transformation into red, quiescent ellipticals or star-forming spirals. The study of cosmic accretion shocks is also central to understanding the dark energy component of the universe. Dark energy is the mysterious force that is driving the accelerated expansion of the universe, and although it remains largely theoretical, shockwaves play a role in helping us understand the forces that influence the universe's expansion. Some of the shocks that take place during galaxy formation can serve as clues about the interplay between dark energy, dark matter, and visible matter, offering indirect insights into the nature of dark energy itself. Cosmic accretion shocks, by altering the distribution and behavior of matter, could provide important evidence for theories about the accelerated expansion and the structure of the universe. For years, scientists have been using simulations and theoretical models to better understand the role of these shocks in shaping the universe. Supercomputers allow for the creation of sophisticated models that simulate the complex dynamics of accretion shocks within galaxy clusters. These simulations provide a way to predict what happens when matter falls into a gravitational well, what types of shockwaves are generated, and how these shocks influence the temperature, density, and magnetic fields within these regions. By comparing these simulations with actual observational data, scientists are able to test their theories and refine their models. In addition to supercomputer simulations, the field of observational astronomy has made significant advancements in detecting the effects of cosmic shocks. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the upcoming James Webb Space Telescope, JWST, are set to provide unprecedented views of galaxy clusters and the shockwaves within them. These next-generation telescopes will allow astronomers to observe the intricacies of shock-induced star formation, the evolution of magnetic fields, and the behavior of gas in the most extreme environments. The Cosmic Microwave Background (CMB) radiation, which provides a snapshot of the early universe, is another key observational tool for understanding cosmic accretion shocks. The CMB carries information about the density fluctuations in the early universe, which were eventually amplified by gravity, leading to the formation of galaxies and clusters. By analyzing the CMB, scientists can trace the origins of these fluctuations and better understand the conditions that gave rise to cosmic shocks. This provides a direct link between the early universe and the more evolved state we observe today. Cosmic accretion shocks are at the heart of many of the processes that shape the universe. They influence the formation and evolution of galaxies, regulate the behavior of black holes, and contribute to the large-scale structure of the cosmos. These shocks are responsible for the heating of gas, the acceleration of particles, the creation of magnetic fields, and the triggering of star formation. By studying the role of these shocks, we gain a deeper understanding of the universe's past, present, and future. The mysteries of cosmic accretion shocks are fundamental to our understanding of the universe itself, and as technology advances, we will continue to uncover the secrets they hold. As we continue to unravel the complexities of cosmic accretion shocks, it becomes evident that they play a fundamental role not just in shaping the structures we observe today but in driving the evolution of the entire cosmos. These shockwaves are not isolated events. They are interconnected with nearly every cosmic phenomenon we can observe, from the formation of galaxies to the fueling of supermassive black holes. One of the key aspects that make accretion shocks so fascinating is their ability to trigger a range of different processes, from star formation to the acceleration of particles to nearly the speed of light. This process of particle acceleration, often linked to cosmic rays, serves as a gateway to understanding some of the highest energy phenomena in the universe. Cosmic rays are highly energetic particles that travel across vast distances, potentially originating from distant galaxy clusters or active galactic nuclei. They are largely composed of protons and atomic nuclei, and they often carry energies millions of times higher than particles produced in terrestrial particle accelerators. Cosmic accretion shocks are believed to be responsible for the acceleration of these particles, as the shockwaves generated by accreting matter can convert kinetic energy into high-energy particles. In the case of galaxy clusters, the interaction between shockwaves and the surrounding gas can also lead to the creation of cold fronts. These cold fronts are regions where the temperature of the gas drops rapidly, creating sharp boundaries between hot and cold gas. The study of these cold fronts, particularly in galaxy clusters, has become an important tool for understanding the dynamics of accretion shocks. The way that cold fronts form and evolve is a direct result of the intricate balance between gravitational forces, shock heating, and the properties of the gas itself. As the shockwaves propagate through the gas, they can either compress or dilute regions of the cluster, leading to the formation of these cold fronts. These cold fronts provide a valuable glimpse into the inner workings of galaxy clusters. By studying them, astronomers can learn more about the distribution of gas, the presence of dark matter, and the overall structure of these massive cosmic objects. Cold fronts also serve as a laboratory for studying the behavior of gas under extreme conditions, providing insights that are critical for understanding other astrophysical phenomena, such as star formation and the fueling of supermassive black holes. Moreover, the interaction of cosmic accretion shocks with magnetic fields in galaxy clusters cannot be overstated. Magnetic fields are present in virtually all cosmic environments, from the diffuse gas in galaxy clusters to the high-energy jets emitted by active galactic nuclei. These fields are shaped and modified by the passage of shockwaves, often leading to the formation of complex structures. For instance, shock-driven turbulence can amplify magnetic fields, creating regions of intense field strength that influence the motion of charged particles within the cluster. This effect can lead to the formation of structures like magnetic filaments, and even contribute to the creation of cosmic jets that stretch across millions of light years. These cosmic jets, which are often associated with supermassive black holes, are powerful outflows of matter and energy that are thought to be driven by the accretion process. The shockwaves generated by the accretion of matter onto the black hole can propel material at nearly the speed of light, creating collimated jets that can extend well beyond the host galaxy. The study of these jets, and the shocks that fuel them, is essential for understanding the growth and behavior of supermassive black holes, as well as their impact on the surrounding galaxy. The shock-driven processes within galaxy clusters also have significant implications for the overall evolution of large-scale cosmic structures. As shocks propagate through clusters, they can alter the temperature and density profiles of the gas, influencing the dynamics of the entire cluster. This has important consequences for our understanding of galaxy cluster formation, as well as the role that these clusters play in the larger cosmic web. The cosmic web, a vast network of galaxy clusters and filaments that spans the universe, is shaped by the interactions between dark matter, gas, and shockwaves. The gravitational collapse of gas clouds into dark matter halos leads to the formation of these massive structures, which are held together by the invisible hand of gravity. However, the dynamics of this process are far from straightforward. Shockwaves are responsible for much of the heating and redistribution of gas within these clusters, playing a central role in determining their final shape and structure. The intricate interplay between shocks, magnetic fields, and gas dynamics is what ultimately determines the evolution of the cosmic web. Additionally, these shock-driven processes are not confined to just galaxy clusters. They also affect the intergalactic medium, IGM, the diffuse gas that exists between galaxies. The IGM is a crucial component of the universe, as it connects galaxies and clusters in a vast network of material. The shockwaves generated during the formation of galaxies and clusters can propagate through the IGM, heating the gas and altering its density. This heating process plays a significant role in regulating the thermal state of the IGM, and is thought to have been a major factor during the era of cosmic reionization, when the first stars and galaxies began to light up the universe. The concept of cosmic reionization, which occurred roughly 1 billion years after the Big Bang, is intrinsically tied to the role of accretion shocks. During this period, the universe transitioned from being opaque to transparent as the first stars and galaxies began to ionize the surrounding hydrogen gas. The shockwaves created during the formation of these early structures contributed to this reionization process by heating the gas and making it more ionized. This, in turn, allowed for the formation of the first large-scale structures, such as the earliest galaxies, and played a crucial role in the evolution of the universe. Looking further into the future, the continued study of cosmic accretion shocks will be essential for understanding the fate of the universe. As the universe continues to expand, the effects of these shocks will persist, shaping the evolution of galaxies, clusters, and the cosmic web. The role of dark energy, which is driving the accelerated expansion of the universe, will likely interact with these shocks in ways that we are only beginning to understand. The balance between shock-driven processes and the influence of dark energy could ultimately determine the long-term evolution of cosmic structures. Future advancements in observational technology, particularly with the advent of next-generation telescopes like the James Webb Space Telescope, will provide new insights into the role of cosmic accretion shocks. These instruments will allow us to observe the most distant galaxies and clusters, providing a deeper understanding of the processes that shaped the early universe. By studying these processes in greater detail, we may uncover new mysteries that shed light on the fundamental forces that govern the cosmos. The role of cosmic accretion shocks in shaping the universe is profound and far-reaching. These shockwaves influence everything from the formation of galaxies and clusters to the behavior of black holes and the acceleration of cosmic rays. They are central to understanding the large-scale structure of the universe and play a critical role in the ongoing evolution of cosmic objects. As our observational capabilities continue to advance, we will uncover even more about the intricate interplay between shock-driven processes and the other forces that govern the universe. The mysteries surrounding cosmic accretion shocks are far from fully understood, but they remain one of the most exciting and essential areas of astrophysical research. As we delve deeper into the intricacies of cosmic accretion shocks, the revelation that these shockwaves are more than just passive phenomena begins to sink in. They are active participants in the very formation and evolution of cosmic structures. Not just in the present universe but throughout its entire history, from the earliest moments after the Big Bang, when the first galaxies began to coalesce, to the ongoing formation of galaxy clusters. The impact of cosmic accretion shocks cannot be overstated, for they shape the universe in ways that are often overlooked. Let's take a closer look at the role these shocks play in galaxy formation. The process begins with the collapse of gas clouds under the influence of gravity. As these clouds condense, they create regions of extremely high density, leading to the formation of stars, and eventually, galaxies. However, this collapse doesn't happen in a smooth, orderly manner. Rather, as the gas compresses, it generates shockwaves that ripple through the surrounding material. These shocks heat the gas, preventing it from cooling too rapidly and thus regulating the rate at which stars form. The balance between heating and cooling within the collapsing gas clouds is one of the key factors that determines whether a region will form stars at a rapid pace or whether the gas will disperse without forming new stars at all. These shocks also play a critical role in regulating the energy output of galaxies. As gas falls toward the supermassive black holes at the centers of galaxies, it generates enormous amounts of energy in the form of radiation, which is often released as a result of accretion. This energy is what powers the brightest and most energetic phenomena in the universe, such as active galactic nuclei, AGN, and quasars. The shockwaves produced during accretion events around black holes are thought to be the driving force behind the release of this radiation, as the shock-heated gas is rapidly accelerated and heated to extreme temperatures. In addition to this, cosmic accretion shocks are instrumental in regulating the mass growth of galaxies. As galaxies merge and interact with one another, their gas content is funneled toward the center of the galaxy, where it can be heated and compressed by shockwaves. This process not only contributes to the growth of the central black hole, but also fuels the ongoing star formation within the galaxy. It's a delicate balance. Without the heat provided by the shocks, the gas would cool too quickly, halting star formation. But if the shocks are too powerful, they can prevent gas from reaching the center of the galaxy entirely, stifling growth and star formation altogether. Another intriguing aspect of cosmic accretion shocks is their impact on the intergalactic medium, IgM. The IgM is the diffuse gas that exists between galaxies, making up the majority of matter in the universe. It is often extremely hot and thin, making it difficult to study directly. However, the shockwaves created by accretion events in galaxy clusters can have a profound effect on the IgM, heating it to temperatures of millions of degrees and contributing to the overall warm-hot gas that exists between galaxies. This heating process plays a role in the ongoing evolution of the IgM, driving the development of large-scale cosmic structures such as the cosmic web. The cosmic web itself is a vast network of interconnected galaxy clusters and dark matter, forming a spiderweb-like structure that spans the universe. It is in this web that the most fundamental processes of the universe play out, from the formation of stars and galaxies to the evolution of the largest structures in the cosmos. The shockwaves created by the collapse and accretion of matter in galaxy clusters contribute to the development of this cosmic web, shaping its overall structure and determining the location of galaxies within it. The interplay between shock-driven processes and the gravitational forces that govern galaxy formation is what ultimately determines the distribution of matter throughout the universe. As we zoom out even further, the effects of cosmic accretion shocks extend beyond individual galaxies and clusters. They shape the very large-scale structure of the universe itself. This structure is dominated by vast voids, regions of space that are sparsely populated by matter, interspersed with dense filaments of galaxies and dark matter that form the cosmic web. The shockwaves that permeate galaxy clusters influence the growth and evolution of these filaments, determining how galaxies are arranged on the largest scales. On the largest possible scale, cosmic accretion shocks are responsible for creating the fundamental structure of the universe. From the distribution of galaxies to the clustering of dark matter, the shockwaves that arise from the accretion of gas and matter set the stage for the formation of the cosmos as we know it. As the universe continues to expand, these shocks will continue to shape the future evolution of cosmic structures, ensuring that the universe remains a dynamic, ever-changing place. In terms of the ongoing cosmic evolution, shocks can also be key players in the broader context of dark energy. Dark energy, the mysterious force responsible for the accelerated expansion of the universe, interacts with the cosmic structures formed by accretion shocks. The accelerated expansion has vast consequences for the universe's future, particularly in how the matter within it is distributed and structured. Cosmic accretion shocks, in turn, may provide insights into how these large-scale structures behave in a universe expanding at an ever-increasing rate. Furthermore, the study of cosmic accretion shocks is crucial for understanding the nature of cosmic inflation, an event that occurred just fractions of a second after the Big Bang and caused the universe to expand at an exponential rate. Though the inflationary period is not directly tied to shocks, it set the stage for the formation of the structures that shocks now shape. The imprint of this early, rapid expansion can still be seen in the distribution of galaxies and clusters across the universe today. The effects of cosmic accretion shocks are not just limited to the present day. Their influence stretches back to the very beginnings of the universe, and in some ways, the shocks we observe today are echoes of processes that began billions of years ago. The very formation of the first galaxies, the merging of star clusters, and the eventual creation of the large-scale structures we see in the universe today all trace their origins back to the role of shockwaves in the early universe. As we continue to observe these shocks through telescopes like the Chandra X-ray Observatory, the James Webb Space Telescope, and the upcoming missions in space exploration, we are beginning to piece together the cosmic puzzle. By studying these shocks, we are not only learning about the forces that shape the universe at large but also gaining insight into the fundamental physical processes that govern all of nature, from the behavior of gas and particles to the dynamics of galaxy formation and the evolution of large-scale cosmic structures. Thus, while the mysteries of cosmic accretion shocks are far from fully understood, what we do know is clear: they are a cornerstone of cosmic evolution. The future holds exciting possibilities for understanding the true nature of these shockwaves and the critical role they play in shaping the universe's past, present, and future. With advancements in technology and observational methods, we will continue to explore these forces, expanding our understanding of the universe and uncovering new mysteries that lie at the heart of cosmic structure. The role of cosmic accretion shocks has far-reaching implications not only for the development of large-scale cosmic structures but also for our understanding of fundamental astrophysical processes. When we examine the evolution of galaxies and clusters, it's crucial to recognize that the gas involved in their formation is not just a passive component, it is actively interacting with its environment through shock-driven processes that govern its temperature, density, and velocity. The shock heating of gas, for example, is responsible for creating the hot, diffuse gas found in galaxy clusters. These clusters are among the largest gravitationally bound structures in the universe, and their formation is deeply intertwined with the shocks that arise as gas accretes into these regions. As gas is pulled inward by the intense gravitational forces of the cluster's dark matter, it is heated by shocks generated during the accretion process. The gas then forms a dense, hot plasma known as the intracluster medium, ICM, which can reach temperatures of several million degrees Kelvin. This hot gas emits X-rays, allowing astronomers to study the ICM and uncover details about the shock processes involved. In galaxy clusters, these shocks have a profound impact on the dynamics of the cluster as a whole. For instance, the shocks play a significant role in regulating the energy balance within the cluster. They can transport heat across vast distances, smoothing out temperature variations and preventing the gas from cooling too quickly. Without these shocks, the gas would cool rapidly, leading to a suppression of star formation. Shocks, however, provide the energy needed to prevent this cooling, ensuring that the gas remains hot enough to fuel the ongoing activity of galaxies within the cluster. One of the most compelling aspects of cosmic accretion shocks is how they influence the feedback mechanisms within galaxies. These feedback loops, often driven by supermassive black holes at the centers of galaxies, can have profound effects on the surrounding gas. When material falls toward the supermassive black hole, it can be heated to extremely high temperatures, generating powerful jets and outflows that disrupt the surrounding gas. These shock-driven outflows inject energy into the surrounding medium, preventing further star formation by heating the gas and pushing it away from the galactic center. This process is known as AGN feedback, and it is an essential mechanism in regulating the growth of galaxies and the formation of stars. Interestingly, cosmic accretion shocks are also central to understanding the phenomenon of cosmic entropy. Entropy, in this context, refers to the degree of disorder within the universe, and cosmic shocks are thought to play a role in distributing this disorder throughout the cosmos. When gas undergoes shock heating, its entropy increases as the energy is spread out across larger volumes. This process contributes to the overall entropy of the universe and influences the formation of cosmic structures by affecting the thermal history of the gas. Another key aspect of cosmic accretion shocks is their influence on the formation of the large-scale structure of the universe. The gravitational collapse of matter, driven by dark matter and dark energy, gives rise to the cosmic web, a vast network of interconnected filaments of galaxies and dark matter. Shocks play a critical role in shaping the geometry and dynamics of this cosmic web. As gas flows along the filaments, it experiences shock heating, which can affect how matter accumulates in different regions of space. Over time, this process results in the formation of galaxy clusters and superclusters, which are the largest structures in the universe. The study of cosmic accretion shocks also touches upon some of the most profound questions in cosmology. For example, one of the great mysteries of modern astrophysics is the nature of dark matter. While dark matter has been detected through its gravitational effects, it has never been directly observed. However, cosmic accretion shocks provide an indirect way to study dark matter. The distribution of dark matter within galaxy clusters influences how gas behaves under shock conditions. By studying the shock patterns in these regions, scientists hope to gain insight into the properties of dark matter, potentially revealing new aspects of this enigmatic substance. The role of cosmic accretion shocks extends beyond just the large-scale structure of the universe. They are intricately tied to the formation of cosmic structures at smaller scales, such as individual stars and planetary systems. As gas clouds collapse to form stars, the interactions between gas particles generate shockwaves that heat the surrounding material. These shocks, in turn, play a role in regulating the rate at which stars form, ensuring that gas does not collapse too quickly, which could lead to the formation of excessively large stars, or too slowly, which could result in the cessation of star formation altogether. The study of cosmic accretion shocks also provides valuable insights into the evolution of the early universe. After the Big Bang, the universe was filled with a hot, dense plasma of gas and radiation. Over time, this plasma began to cool and condense, forming the first stars and galaxies. The shockwaves produced by the accretion of matter during this early period played a crucial role in the growth of these first structures. Understanding how these shocks evolved during the early universe is key to unlocking the mysteries of cosmic evolution. cosmic accretion shocks also have implications for understanding the future of the universe. As the universe continues to expand, galaxy clusters and other cosmic structures will continue to evolve. The role of shocks in the evolution of these structures will be crucial in determining the long-term fate of the cosmos. For example, shocks may play a role in the eventual collapse or merger of galaxy clusters, potentially leading to the formation of even larger structures. Alternatively, shocks may help disperse matter throughout the universe, preventing the formation of new structures and contributing to the eventual heat death of the universe. In addition to their role in galaxy and cluster formation, cosmic accretion shocks are also essential for understanding the formation of black holes. Black holes, particularly supermassive black holes, are thought to form in the centers of galaxies as a result of the accretion of gas and matter. The shockwaves produced by this accretion process can play a pivotal role in the growth of black holes, as they help funnel material toward the event horizon. The dynamics of this accretion process, along with the shock heating of the gas, can lead to the formation of powerful jets and radiation that are emitted by black holes, making them some of the most energetic and intriguing objects in the universe. The study of cosmic accretion shocks is still in its early stages, but with the advent of new observational tools and advanced simulation techniques, we are gaining an increasingly detailed picture of how these shocks shape the universe. Observatories such as the Chandra X-ray Observatory, the Hubble Space Telescope, and the James Webb Space Telescope are providing unprecedented insights into the effects of cosmic accretion shocks on galaxy clusters, black holes, and the intergalactic medium. These new observations are allowing scientists to test and refine their theoretical models, providing a deeper understanding of the mechanisms that govern the formation and evolution of cosmic structures. By studying the role of shocks in these processes, we are not only learning about the universe's past but also gaining insights into its future. The mysteries of cosmic accretion shocks are far from fully understood, but every discovery brings us one step closer to unlocking the secrets of the cosmos. As we continue to study these shockwaves and their effects, we may find that they hold the key to some of the deepest questions in cosmology. How did the universe evolve from the Big Bang to the complex, structured cosmos we see today? What are the ultimate fates of galaxies, clusters, and black holes? And how do cosmic shocks interact with dark matter, dark energy, and other fundamental forces of nature? These are the questions that drive us forward in our quest to understand the universe. Cosmic accretion shocks, once thought to be a secondary phenomenon, are now recognized as one of the fundamental forces shaping the cosmos. As we continue to study them, we may uncover new insights that reshape our understanding of the universe and our place within it. The significance of cosmic accretion shocks stretches far beyond the realms of galaxy formation and stellar evolution. They are pivotal in shaping the cosmic landscape by influencing everything from the thermal history of the universe to the behaviors of dark matter and dark energy. These shocks, often overlooked in their early stages of study, are now central to some of the most exciting and challenging areas of modern astrophysics. When it comes to the intergalactic medium, the gas that exists between galaxies, cosmic shocks play a major role in both its heating and its distribution across vast distances. The material that fills the vast voids between galaxies isn't empty space. It's filled with diffuse gas that is often heated by shocks. As the gas is pulled into the gravitational wells of galaxy clusters or superclusters, it can undergo shock heating, raising its temperature to millions of degrees Kelvin. This heated gas, in turn, emits X-rays, which provide a unique opportunity to study the processes that govern the dynamics of the universe on the largest scales. Understanding how shockwaves influence the distribution of gas in the intergalactic medium helps us comprehend not just the distribution of matter, but also the evolution of the cosmic web itself. The cosmic web, the intricate network of galaxies and dark matter that spans the universe, owes much of its structure to shocks. As matter flows along the web's filaments, shockwaves propagate through the gas, altering its temperature, density, and velocity. These shocks can create dramatic changes in the way galaxies interact with one another. In some cases, shock-induced heating can slow down the collapse of gas clouds, which might otherwise result in too rapid a star formation process. In other situations, shocks can trigger a burst of star formation by compressing gas enough to overcome its internal pressure, causing it to collapse and form new stars. It's also critical to explore how cosmic accretion shocks impact the large-scale distribution of dark matter. Though dark matter does not directly interact with light or normal matter, its gravitational influence is undeniable. The shocks created by the accretion of gas and matter into galaxy clusters and superclusters provide a means to study dark matter's behavior indirectly. By observing how gas behaves within these shock-heated environments, scientists can infer the distribution of dark matter in ways that are not possible through direct observation. This process is fundamental in testing and refining our models of dark matter, which remain one of the most significant unresolved mysteries in modern cosmology. The connection between shocks and dark energy is another area of great interest. Dark energy is thought to be responsible for the accelerated expansion of the universe, but its exact nature is still largely unknown. Some cosmologists speculate that shocks could provide clues to understanding dark energy's role in shaping the expansion of the universe. For instance, the way shockwaves behave in various regions of space could offer new insights into how dark energy interacts with the fabric of spacetime. The expansion of the universe, as driven by dark energy, might even influence how shockwaves propagate through space, potentially offering a link between two of the most enigmatic forces in the cosmos. While cosmic shocks have a profound influence on the evolution of large-scale cosmic structures, their effects are also felt at much smaller scales. One of the most intriguing phenomena associated with shock heating is the formation of stellar remnants, such as white dwarfs, neutron stars, and black holes. As gas is accreted into these objects, it undergoes intense shock heating, leading to the creation of extremely high-energy environments. For instance, in the case of a black hole, the accreting gas is heated to such an extent that it emits powerful radiation in the form of X-rays, gamma rays, and even neutrinos. These shock-driven emissions are not only detectable from Earth but can also provide critical information about the black hole's environment, such as its spin, mass, and growth rate. Moreover, shockwaves are also involved in some of the most energetic events in the universe. The formation of supernovae, the explosive death of massive stars, is driven in large part by shockwaves that propagate outward from the collapsing core of a star. These shockwaves are responsible for triggering the explosion that disperses the star's outer layers into space, enriching the surrounding environment with heavy elements. Supernovae are critical in the context of cosmic evolution, as they produce many of the elements essential for life and play a key role in triggering the formation of new stars and planetary systems. Another significant event in the universe that is tied to cosmic accretion shocks is the phenomenon known as cosmic reionization. This event, which took place around 1 billion years after the Big Bang, marked the period when the first stars and galaxies began to form and emit ultraviolet radiation. This radiation ionized the hydrogen gas that permeated the universe, leading to the reionization of the intergalactic medium. The shocks that occurred during this period, as matter began to accrete into the first large structures, played a key role in driving the reionization process. By studying these shocks, scientists hope to gain insights into the conditions that existed in the early universe and how they led to the formation of the first galaxies and stars. As the universe continues to expand and evolve, cosmic accretion shocks will remain a central focus of research. New advancements in technology and observation techniques will allow scientists to probe these shocks in increasingly detailed ways. Instruments such as the next-generation X-ray observatories and future space telescopes will provide even clearer views of how shocks shape the evolution of the universe. Through simulations, astronomers will be able to model the behavior of shocks in unprecedented detail, helping to refine our understanding of how these processes operate on both large and small scales. In addition to these theoretical and observational advancements, the study of cosmic accretion shocks has important implications for broader fields of physics and cosmology. For example, understanding the dynamics of shocks can improve our knowledge of magnetohydrodynamics, MHD, which deals with the behavior of conductive fluids in the presence of magnetic fields. Since much of the gas in space is ionized and conductive, The study of shockwaves can help us understand how magnetic fields influence the behavior of cosmic gases and how these fields are shaped by large-scale shocks. This understanding is essential for developing more accurate models of how magnetic fields interact with cosmic structures, which could, in turn, reveal new information about the evolution of the universe. Furthermore, the study of cosmic accretion shocks can help improve our understanding of the interconnection between different physical processes. Shocks do not operate in isolation, they interact with other phenomena, such as turbulence, gravitational waves, and magnetic fields. The interaction between these processes can lead to a rich variety of outcomes, and studying them together provides a more holistic view of the universe. For example, understanding how shocks interact with turbulence in galaxy clusters can help explain the distribution of matter within these clusters, while the relationship between shocks and gravitational waves may lead to new insights into the nature of spacetime itself. Cosmic accretion shocks are far from a niche topic within astrophysics. They are central to our understanding of the universe's past, present, and future. By examining the role of these shockwaves, scientists gain insights into everything from the formation of galaxies to the behavior of dark matter, dark energy, and black holes. As we move forward in the study of cosmic accretion shocks, we can expect to uncover even more profound discoveries that challenge our current understanding of the universe and deepen our connection to the cosmos. As we continue to explore these mysteries, one thing is certain: the role of cosmic accretion shocks in the formation and evolution of the universe is far from fully understood. Every new observation, every new simulation, and every new discovery brings us one step closer to understanding how these dynamic forces shape the cosmos. In the end, cosmic accretion shocks may be one of the most essential keys to unlocking the secrets of the universe, providing answers to some of the most profound questions in astrophysics. As our understanding of cosmic accretion shocks continues to evolve, one of the most exciting areas of research lies in the interplay between these shocks and the broader structure of the universe. This is not just a matter of studying individual galaxies or galaxy clusters in isolation, but rather understanding how these objects and their surrounding environments are interconnected. When gas is funneled into galaxy clusters through the cosmic web, it is subjected to a variety of physical forces, including gravitational, thermal, and shock-driven forces. The interaction between these forces can result in complex and unpredictable behavior, which is why researchers are so interested in studying the detailed dynamics of accretion shocks. One of the key phenomena that can emerge from the combination of shock waves and gravitational forces is what is known as shock reionization. As we mentioned earlier, cosmic reionization refers to the process by which the universe transitioned from being filled with neutral hydrogen gas to being dominated by ionized gas. This process occurred about 1 billion years after the Big Bang. It was driven by the radiation emitted by the first stars and galaxies, which ionized the hydrogen gas that was present at the time. However, it is now believed that the shocks created by the accretion of matter into early galaxy clusters played an important role in this process. These shocks caused the gas to be heated to extremely high temperatures, which, in turn, helped to ionize the surrounding hydrogen gas. The shock-driven heating provided a catalyst for the onset of reionization, accelerating the process and making it more widespread across the universe. Studying how these shocks influence reionization helps scientists better understand the early stages of galaxy formation and how the first stars began to light up the universe. But shockwaves don't just play a role in the formation of galaxies and the intergalactic medium, they also help shape the structure of the galaxies themselves. For instance, the shock waves generated during the accretion of gas into a galaxy can cause the gas to collapse, resulting in the formation of dense regions known as galactic disks. These disks are the birthplace of stars, and their formation is often accompanied by violent shock interactions that can drive powerful outflows of gas and even trigger the formation of supermassive black holes at the centers of galaxies. In addition to their role in star formation, shocks also have a significant impact on the properties of the gas within galaxies. The shock-heated gas, for example, can lead to the creation of cold fronts and other phenomena that affect how galaxies interact with their environments. These cold fronts are regions of gas that have been cooled by the shockwave and can be seen as thin, dark lines in observations of galaxy clusters. These cold fronts can reveal important information about the dynamics of gas flow and the role of shocks in shaping the evolution of galaxies. Furthermore, the presence of shocks in galaxies and galaxy clusters can affect the growth and evolution of supermassive black holes. These black holes, which reside at the centers of most large galaxies, are believed to have formed in tandem with their host galaxies, and their growth is closely tied to the accretion of gas. When gas is pulled toward a black hole, it often encounters shockwaves that heat it up to extremely high temperatures. This process can lead to the formation of powerful jets and outflows of matter, which in turn influence the surrounding galaxy. Studying how shocks influence the behavior of supermassive black holes is crucial for understanding the growth and evolution of these enigmatic objects. While much of the focus of shock research has been on the role of shocks in the formation of galaxies and large-scale cosmic structures, shocks also play a vital role in the larger cosmological context. In particular, shocks are a key factor in the formation of cosmic voids, the vast regions of space that are largely devoid of galaxies and other matter. These voids are believed to have formed as a result of the expansion of the universe and the collapse of matter into dense regions. The shock waves created during the accretion of gas into galaxy clusters can help create and shape these voids, providing insights into the large-scale structure of the universe and the forces that have shaped it. Another fascinating aspect of cosmic shocks is their potential role in the creation of cosmic magnetic fields. Magnetic fields are ubiquitous in the universe, and they play a central role in a variety of astrophysical processes, from the behavior of interstellar gas to the dynamics of galaxy clusters. Shockwaves, as we know, can generate turbulent motions within the gas, and these turbulent motions can amplify existing magnetic fields. The shocks that occur during galaxy and cluster formation could therefore play a major role in the creation and evolution of cosmic magnetic fields. This area of research is still in its infancy, but it holds great promise for understanding the nature of cosmic magnetism and how it influences the behavior of the universe. As we continue to explore the mysteries of cosmic accretion shocks, it's clear that these phenomena are not just interesting in isolation. They are a central piece of the puzzle that is the universe. From the formation of galaxies to the behavior of supermassive black holes and the dynamics of cosmic magnetic fields, shocks play a vital role in shaping the cosmos. The study of these shocks offers us an opportunity to unlock new insights into the fundamental forces that govern the universe, and it brings us one step closer to answering some of the most profound questions in astrophysics. One of the most exciting prospects for the future is the ability to study cosmic accretion shocks in even greater detail. With the development of new observational techniques and space-based telescopes, scientists are now able to study shock-heated gas in unprecedented detail. Instruments like the James Webb Space Telescope and the upcoming X-ray observatories will provide even deeper insights into the processes that govern cosmic shocks. These tools will allow researchers to probe the behavior of shockwaves in galaxy clusters, supernova remnants, and even the accretion disks around black holes, providing a wealth of data that will shape the next generation of astrophysical models. Simulations are also becoming increasingly powerful, allowing scientists to model the behavior of cosmic shocks across a range of different environments and scales. These simulations, which use advanced numerical techniques and high-performance computing, enable researchers to explore how shocks interact with other physical processes, such as turbulence, magnetic fields, and gravitational waves. By combining observational data with these simulations, scientists are able to test and refine their theories about how cosmic shocks shape the evolution of the universe. The implications of understanding cosmic accretion shocks extend far beyond the confines of astrophysics. These phenomena are intimately tied to the fundamental forces that govern the universe, and they offer a unique window into the mysteries of the cosmos. By studying cosmic shocks, we not only gain insights into the large-scale structure of the universe but also deepen our understanding of the nature of matter, energy, and the fundamental forces of nature. As we look ahead, one thing is certain: the study of cosmic accretion shocks is a field that will continue to yield profound discoveries for years to come. Whether it's through observations of galaxy clusters, simulations of black hole accretion disks, or studies of the intergalactic medium, shocks will remain a central focus of research in cosmology. They are not just a piece of the cosmic puzzle, they are a key that will unlock many of the universe's deepest secrets. As we move forward in the study of cosmic accretion shocks, it's important to consider how these phenomena fit into the broader framework of cosmological evolution. Over billions of years, the universe has transformed from a hot, dense state to the vast, expanding cosmos we see today. This transformation is driven by a complex interplay of forces, and shocks are at the heart of many of these processes. Whether it's through the heating of gas in galaxy clusters or the role of shocks in the formation of cosmic voids, the influence of these phenomena is both far-reaching and profound. One of the most compelling aspects of cosmic accretion shocks is their ability to shape large-scale structures within the universe. These structures, such as galaxies, galaxy clusters, and the cosmic web, are not static. They are constantly evolving, with matter flowing through them, interacting, and changing in response to gravitational, thermal, and shock-driven forces. Shocks are responsible for much of this evolution, as they play a key role in regulating the flow of gas and matter within galaxies and clusters, influencing everything from star formation to the growth of supermassive black holes. In particular, shocks are thought to play a critical role in the process of feedback within galaxies. This refers to the way in which the energy and momentum injected into a system can affect its future evolution. When gas is accreted onto a galaxy or black hole, it often experiences shocks that release enormous amounts of energy. This energy can be transferred to the surrounding gas, causing it to heat up and potentially be expelled from the system entirely. This process, known as thermal feedback, can have profound consequences for the growth of galaxies and the surrounding intergalactic medium. One of the key challenges in studying cosmic accretion shocks is understanding how these phenomena interact with the broader environment. For example, the energy released by shocks can affect the dynamics of the surrounding gas, potentially leading to the formation of new structures such as cold fronts or shock fronts. These features are thought to be the result of the complex interplay between shock-driven heating and the gravitational collapse of gas. Understanding how these interactions shape the evolution of galaxies and galaxy clusters is a major area of ongoing research. Recent advances in observational techniques have allowed scientists to study the effects of shocks in greater detail than ever before. With the advent of space-based telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory, astronomers can now observe shock-heated gas in distant galaxies and clusters, allowing them to map the distribution and behavior of shocks across the universe. These observations are helping to refine our understanding of how shocks influence galaxy formation and the larger cosmic structure. At the same time, simulations of cosmic accretion processes are becoming more sophisticated, incorporating increasingly detailed models of gas dynamics, shock formation, and the effects of magnetic fields. These simulations allow researchers to test different hypotheses about the role of shocks in shaping cosmic structures, helping to refine our understanding of the processes that drive the evolution of the universe. Perhaps one of the most exciting areas of research is the study of how shocks influence the formation of large-scale structures such as cosmic voids. These vast, empty regions of space are some of the most enigmatic features of the universe. Understanding how shocks contribute to their formation and evolution is key to unlocking the mysteries of the universe's large-scale structure. It is thought that shocks, by redistributing matter and energy, play a key role in creating these voids, which in turn influence the behavior of galaxies and clusters within them. Another fascinating aspect of cosmic accretion shocks is their potential role in the creation of cosmic magnetic fields. Magnetic fields are thought to play a key role in many astrophysical processes, from the behavior of interstellar gas to the dynamics of galaxy clusters. Shocks, by driving turbulence within the gas, can amplify existing magnetic fields, potentially leading to the formation of large-scale cosmic magnetic structures. Understanding how shocks interact with magnetic fields is an emerging field of study, with researchers working to uncover the details of this complex relationship. As we continue to explore these cosmic phenomena, it's clear that our understanding of the universe is only beginning to scratch the surface. The study of cosmic accretion shocks is an essential part of this journey, providing valuable insights into the forces that govern the cosmos. Whether through detailed observations of distant galaxies or sophisticated simulations of accretion processes, the study of shocks is providing new answers to some of the most fundamental questions in astrophysics. The implications of this research extend far beyond our understanding of galaxy formation and the behavior of matter in the universe. By studying the role of cosmic shocks in shaping large-scale structures, we are gaining a deeper understanding of the fundamental processes that govern the evolution of the universe. These insights not only inform our knowledge of cosmic evolution, but also provide a glimpse into the nature of the forces that shape the universe as we know it. In addition to their scientific importance, the study of cosmic shocks has practical implications for the development of new technologies. The complex dynamics of gas and matter within galaxies and clusters can offer valuable lessons for engineers and scientists working on advanced technologies, from plasma physics to energy generation. By studying how shockwaves interact with matter on cosmic scales, researchers are learning more about the behavior of matter under extreme conditions, which could have applications in fields ranging from fusion energy to space travel. As we look to the future, it's clear that the study of cosmic accretion shocks will continue to play a central role in our understanding of the universe. With the launch of next-generation observatories and the continued development of computational simulations, researchers are poised to uncover even more about these enigmatic phenomena. By pushing the boundaries of our understanding, we are one step closer to answering the fundamental questions about the nature of the universe, the forces that govern it, and the role of cosmic shocks in shaping the cosmos. The mysteries of cosmic accretion shocks are far from being fully understood, and as we continue to explore these phenomena, new questions are sure to arise. How do shocks interact with dark matter and dark energy, two of the most elusive components of the universe? What role do they play in the evolution of galaxy clusters and supermassive black holes? These questions, and many others, remain at the forefront of scientific inquiry. The study of cosmic shocks is a field that will continue to yield new insights into the nature of the universe for years to come. Whether it's through the analysis of shock-heated gas in galaxy clusters or the study of shock-induced magnetic fields, each new discovery brings us closer to understanding the fundamental processes that drive the evolution of the cosmos. The role of cosmic accretion shocks in shaping the universe is a story that is still being written. With each new observation, each new simulation, and each new breakthrough, we uncover a little more about the vast and complex processes that govern the cosmos. And with each new discovery, we come one step closer to answering the ultimate question: what is the true nature of the universe, and how did it come to be? As we continue to explore the intricacies of cosmic accretion shocks, we move deeper into understanding how these phenomena are not only essential to the evolution of galaxies but also to the behavior of the intergalactic medium. The process of cosmic accretion, wherein gas and matter fall into the gravitational pull of massive objects like galaxies and black holes, is inherently tied to the formation of these shocks. As gas is funneled toward these dense regions, it is compressed, heated, and accelerated, producing powerful shock waves that shape the very structure of the universe. These shocks, occurring in regions of space where vast amounts of gas and matter are being pulled together, have a profound impact on the physical characteristics of the surrounding environment. In the dense centers of galaxy clusters, for example, shock fronts can create areas of extremely high temperatures, influencing the overall dynamics of the cluster. As matter gathers, the gas experiences compression and heating, causing it to radiate energy in the form of X-rays. This radiation, detected by space-based telescopes, provides valuable insights into the state of the gas and the shock processes at work. But what about the larger picture? What does the role of cosmic accretion shocks tell us about the universe as a whole? In a sense, these shocks are the backbone of cosmic evolution, acting as the catalysts for structure formation on the grandest scales. Without shocks, the process of galaxy formation would be drastically different. Shocks facilitate the flow of gas into galaxies and provide the necessary pressure to allow for the growth of massive structures. By influencing the way gas behaves under extreme conditions, shocks also affect the formation of stars and supermassive black holes, which are critical components of cosmic evolution. The influence of shocks extends beyond galaxy clusters and into the voids of space, the vast, empty regions that appear to be devoid of matter. Cosmic voids are not just empty spaces. They represent areas where matter has been redistributed by the gravitational and shock-driven forces within the universe. In fact, the very formation of voids is thought to be heavily influenced by the shock-driven dynamics of cosmic accretion. As gas and matter are funneled into galaxy clusters and other dense regions, they leave behind vast, empty regions of space, which can be studied to better understand how the universe is organized on the largest scales. One of the most profound effects of shocks is their ability to influence the energy balance of galaxy clusters. When gas is shock-heated to extremely high temperatures, it can experience dramatic changes in pressure and density. These changes affect the way gas moves and the rate at which it cools, which in turn has a direct impact on star formation and the overall growth of galaxies. Shocks can create turbulent environments in which stars and other cosmic objects are formed and destroyed, leading to the dynamic, ever-changing nature of the universe. The energy released during the shock process can also have far-reaching consequences. In some cases, the energy can be enough to disrupt the balance of forces in the surrounding environment. This can lead to the creation of new structures, such as cold fronts or shock fronts, which are thought to play a key role in the growth of galaxies. As gas is heated and compressed, it can also be ejected from the system, affecting the overall distribution of matter within the cluster. This phenomenon, known as feedback, has important implications for the evolution of galaxies and their surrounding environments. As the field of astrophysics advances, scientists are gaining new tools and techniques to study cosmic accretion shocks in unprecedented detail. With the help of powerful space telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, researchers are able to observe distant galaxies and clusters, providing a deeper understanding of the shock processes that shape the universe. These observations are allowing scientists to test existing models and refine our understanding of how cosmic shocks influence the evolution of the cosmos. Simultaneously, advancements in computational simulations are enabling scientists to model the behavior of gas and matter in response to shocks with increasing accuracy. These simulations, which take into account complex factors such as gravitational forces, gas dynamics, and magnetic fields, allow researchers to study the effects of shocks on both small and large scales. By comparing these simulations with observational data, scientists can test hypotheses and improve our understanding of the role of shocks in cosmic evolution. Looking ahead, it's clear that the study of cosmic accretion shocks will continue to provide critical insights into the nature of the universe. From understanding the formation of galaxies and clusters to unraveling the mysteries of cosmic voids, these phenomena are central to our understanding of how the cosmos came to be. As new discoveries are made and new technologies are developed, we will continue to learn more about the forces that shape the universe and the role that cosmic shocks play in this grand process. But there is still so much we don't know. Despite the significant progress that has been made in studying cosmic shocks, many questions remain unanswered. For instance, how do these shocks interact with dark matter, a mysterious substance that makes up most of the mass in the universe but has yet to be directly detected? What role do these shocks play in the formation and growth of supermassive black holes, which are thought to lie at the center of most galaxies? How do cosmic shocks influence the evolution of the cosmic web, the vast network of filaments that connects galaxies and clusters across the universe? In addition to these fundamental questions, there are also more technical challenges that researchers must address in order to gain a deeper understanding of cosmic accretion shocks. For example, while we have made significant strides in understanding the basic physics of shocks, there is still much to learn about how different types of shocks, such as those occurring in the hot gas of galaxy clusters or those formed by the interaction of galaxies with intergalactic gas, differ in their behavior and effects. Moreover, the complex interplay between shocks and magnetic fields remains an area of intense research, with scientists working to understand how these fields influence the behavior of shock-heated gas. The study of cosmic accretion shocks is a fascinating and evolving field of astrophysics. These shocks are key players in the formation of galaxies, galaxy clusters, and the broader cosmic structure. They shape the universe in ways that we are only beginning to understand. By studying these processes in greater detail, scientists are unlocking the mysteries of the cosmos, offering new insights into the forces that govern the universe and how it has evolved over time. As we continue to make progress in this area, we will undoubtedly uncover even more about the complex, interconnected nature of the universe and the role that cosmic shocks play in its evolution. The role of cosmic accretion shocks becomes even more fascinating when we consider their impact on the large-scale structure of the universe. The cosmic web, an intricate network of galaxy clusters and filaments, is largely shaped by the forces at play during the accretion of gas and matter. These shocks help to define the boundaries and dynamics of the cosmic web, ensuring that galaxies are not randomly scattered but are instead organized in patterns that span vast distances. The formation of these filaments is an incredible process that combines gravitational forces with the high-energy interactions of cosmic shocks. As gas and matter flow into regions of space, they are stretched into long, narrow threads that form the backbone of the cosmic web. Shock waves propagate through these filaments, creating areas of intense pressure and temperature that affect the distribution of gas. This interaction, in turn, influences the formation of galaxy clusters, which are the most massive structures in the universe. At the intersections of these cosmic filaments, where multiple shocks converge, galaxies are often born. The gas in these regions becomes denser, and the temperature increases, triggering the formation of stars and even supermassive black holes. The high-energy processes occurring during these shocks play a crucial role in the dynamics of star formation, determining how much gas is available for stars to form, and how those stars evolve over time. But the cosmic web is not just a passive structure, it is a dynamic environment in which galaxies grow, collide, and evolve. As galaxies move through the cosmic web, they experience shocks from the surrounding gas, which can lead to the accretion of more material, the heating of gas, and the disruption of star-forming regions. These interactions can have profound effects on the development of individual galaxies, leading to the creation of new stars, the destruction of old ones, and even the triggering of active galactic nuclei, AGN. AGN are thought to be powered by supermassive black holes located at the centers of galaxies. The process of accretion onto these black holes generates immense amounts of energy, which can create powerful jets and outflows of material. These energetic events can significantly impact the surrounding galaxy and its evolution. In some cases, the energy released by AGN can drive shocks into the surrounding gas, further influencing the behavior of the galaxy and its environment. This feedback loop, in which cosmic shocks influence the formation of galaxies and black holes, is one of the most exciting areas of modern astrophysics. Interestingly, the study of cosmic accretion shocks also provides us with a window into the early universe. The processes of accretion and shock heating are thought to have played a key role in the formation of the first galaxies and stars. By studying the signatures of these shocks in distant, early universe galaxies, astronomers can learn more about the conditions that existed during the birth of the universe. This kind of research not only sheds light on the origins of galaxies but also helps us understand how the universe has evolved over billions of years. The study of cosmic shocks and their relationship to galaxy formation is also closely tied to the concept of cosmic reionization. This event, which occurred about 13 billion years ago, marks the period when the universe transitioned from being opaque to transparent. During reionization, the first stars and galaxies began to shine, releasing ultraviolet radiation that ionized the surrounding gas. The energy from cosmic shocks likely played a role in this process, heating the gas and facilitating the ionization of hydrogen. Understanding how shocks contributed to reionization is a key piece of the puzzle in understanding the evolution of the early universe. As we continue to delve deeper into the complexities of cosmic accretion shocks, we must also consider their potential connection to dark energy and dark matter. These mysterious components of the universe make up most of its mass energy content, yet their nature remains largely unknown. While cosmic shocks primarily interact with ordinary matter, their effects may extend to dark matter as well. Some theories suggest that dark matter could be affected by the gravitational forces of shocks, which may influence the way it clusters and interacts with visible matter. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, may play a role in the way shocks behave on large scales. The interplay between shocks, dark energy, and dark matter is an exciting frontier in astrophysics that could lead to groundbreaking discoveries about the fundamental nature of the universe. In the quest to understand the full implications of cosmic accretion shocks, we must also consider the role of magnetic fields. These fields are present throughout the universe, influencing the behavior of charged particles and the dynamics of plasma. Shocks can generate strong magnetic fields, which in turn affect the motion of charged particles in the surrounding gas. This interaction between shocks and magnetic fields can lead to the formation of cosmic structures such as magnetic filaments and radio halos. These structures can be observed through specialized instruments, such as radio telescopes, and provide valuable information about the processes at work during cosmic accretion. Furthermore, the role of cosmic shocks in galaxy evolution extends beyond the formation of individual galaxies. As clusters of galaxies form and grow, they experience repeated shock events that can trigger the growth of supermassive black holes and the development of complex intergalactic environments. These repeated shock interactions contribute to the feedback processes that regulate star formation and the distribution of matter within galaxy clusters. The way that cosmic accretion shocks heat and compress gas is also tied to the balance of energy in galaxy clusters. As gas is heated by these shocks, it radiates energy in the form of X-rays, which can be detected by space-based telescopes. This radiation provides crucial insights into the temperature and density of the gas, helping scientists understand the physical properties of the cluster. Additionally, the study of X-ray emission from shock-heated gas can help determine the history of a galaxy cluster, including its age, size, and growth patterns. Ultimately, the study of cosmic accretion shock serves as a crucial piece of the puzzle in understanding the universe's formation and evolution. From the smallest scales of individual galaxies to the vast, interconnected web of cosmic structures, shocks are at the heart of many of the most important processes in astrophysics. As technology advances and our understanding of these phenomena deepens, we will continue to unlock the mysteries of the cosmos, revealing the forces that shape the universe and drive its evolution. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.